What is dark matter, really? Tonight we're settling into a subject that may seem unsettling at first, even though it has quietly existed around us since the very start. It's a concept hiding just outside the limits of human sight, resting in regions where light never truly arrives. We're going to spend a little while exploring the mystery of dark matter, but there's no rush to force conclusions or chase immediate explanations. Instead, we're simply moving gently through the strange nature of this invisible part of the cosmos and why it matters so profoundly. Before we slowly sink deeper into it, I wonder where you're listening from tonight. Is the day already ending where you are? Or are you taking a peaceful break during the afternoon before returning to the responsibilities waiting for you later on? No matter where you happen to be right now, I'm happy you're here, and if this quiet little exploration feels calming or comforting, or simply gives your thoughts a chance to slow down for a while, I'd truly appreciate it if you press the like button or subscribed, because it helps this peaceful corner reach other people who may also need a soft voice accompanying them in the background. Now that we're comfortable, let's quietly drift into the story hidden among the stars. From where we stand, most of the universe appears empty. When you raise your eyes toward the night sky, you notice scattered points of light, tiny glowing specks spread across an immense backdrop that feels more like emptiness than anything real or substantial. It's easy to assume the darkness between those shining points contains absolutely nothing, like a giant blank canvas stretching forever outward. But after decades of careful observation and measurement, astronomers discovered that this darkness is not truly empty space. Something exists there, unseen and silent, never glowing, never reflecting light, never revealing itself directly to human eyes or telescopes. Yet, it still makes its presence known through the one thing it seems capable of affecting: gravity. And gravity, as patient and reliable as ever, always leaves traces behind. That quiet trail of clues is where the story of dark matter truly begins. It began with a quiet question emerging among scientists who realized the universe was not behaving the way it was expected to behave if the only matter that existed was the matter we could directly observe. Stars were traveling in ways that entire clusters of galaxies acted as though they were being held together by something carrying vastly more mass than anything visible within them. These were not tiny irregularities or small calculation errors. They were massive contradictions, and they hinted that something invisible was influencing everything behind the scenes, quietly shaping the architecture of the cosmos without ever revealing itself directly. The earliest clues came from relatively straightforward observations, especially measurements of how quickly stars circle the centers of galaxies. Based on the gravitational laws we understand, stars positioned farther from the galactic center should orbit more slowly than those closer inward. But when astronomers carefully measured their velocities, the results were deeply surprising. The stars near the outer edges were not slowing down at all. Many were moving just as rapidly as stars closer to the middle, and in some situations they were traveling even faster. Under normal circumstances, motion like that should have ripped galaxies apart completely, yet the galaxies remained stable, almost as though some enormous invisible structure was surrounding them and holding everything together. The amount of visible matter inside those galaxies was nowhere near enough to explain such stability. Something else had to be balancing the outward centrifugal force created by those rapidly orbiting stars. The mystery became obvious. What exactly was providing that missing gravity? This was not the sort of puzzle that could be solved simply by building stronger telescopes and looking more carefully into space. Astronomical instruments improved steadily, observations became sharper and more sensitive, and galaxy maps grew increasingly detailed, yet the hidden mass still refused to reveal itself. It did not absorb light. It did not produce light. It did not reflect or scatter light in any detectable way. Nearly every traditional method astronomers relied on for studying distant cosmic objects suddenly became ineffective. Yet, despite this invisibility, the evidence continued growing stronger that something enormous was exerting gravitational influence across the universe. Scientists were forced to approach the mystery indirectly, not by observing the thing itself, but by examining the effects it produced on surrounding matter. Those effects consistently matched the presence of matter that behaves differently from ordinary matter because it does not interact with light in familiar ways. The name dark matter was never meant to sound dramatic or poetic. It was simply the clearest description researchers could offer. It appears to be matter. It appears to be dark. Beyond that, certainty becomes difficult. Even so, despite remaining hidden from direct observation, dark matter seems to shape galaxies at their deepest levels. It acts almost like a cosmic framework or invisible skeleton into which ordinary matter settles as gas, dust, and stars gather together. Without that unseen structure beneath everything, galaxies would not form the way they currently do. Massive galaxy clusters would not behave the way they do. The universe itself would not possess the large-scale appearance we observe today. Dark matter appears to function as the gravitational foundation supporting the visible cosmos, even though humanity has never directly touched it or truly seen it. That idea by itself already feels strange, but the scale of it makes the mystery even more unsettling. Current estimates suggest that dark matter makes up roughly 85% of all matter in existence. That means every visible thing we know, every star, every planet, every nebula, every galaxy cluster, every drifting cloud of dust, every comet, meteorite, and atom inside your own body, inside the device you are listening from, inside every object humanity has ever held or built, represents only a small fraction of what actually exists in the universe. Everything familiar is merely a thin visible surface, layered over an enormous hidden reality, and nearly all of that hidden structure remains completely invisible to the senses humans evolved with. Realizing this changes the way the universe feels in your imagination. Space no longer seems truly empty. Instead, it begins to feel crowded with unseen influence, filled with invisible structure even though it lacks visible light. It is almost like discovering that the people quietly moving props behind a theater stage are not merely assistants helping occasionally, but an enormous hidden workforce, secretly controlling the entire shape and flow of the performance itself. The visible actors may stand beneath the spotlight, but the deeper direction comes from something hidden outside the audience's view. That is the strange perspective dark matter introduces. It does not make the cosmos feel emptier. It makes it feel inhabited by a silent presence, a presence that never glows, never crashes into us, never sends signals through electromagnetic waves, yet still governs the movement of galaxies far larger than human imagination can comfortably grasp. As researchers continued following these clues, their picture of the cosmos slowly transformed. What humanity once assumed was the main structure of the universe turned out to be only the bright decorative layer resting on top of something far greater. If dark matter suddenly vanished, galaxies would begin to come apart. Galaxy clusters would drift away from one another. The immense cosmic web, mapped across billions of light years, with its gigantic filaments and vast empty voids, would collapse into disorder. Dark matter appears to hold that entire structure together, and this hidden architecture is not distributed evenly throughout space. It gathers into patterns and dense regions that function like enormous gravitational valleys, pulling in clouds of gas and dust that eventually become stars, planets, and all the familiar objects filling the visible universe. So even though we cannot observe it directly, we can still follow the marks it leaves on everything that shines. That creates a fascinating connection between what is visible and what is actually true. Human eyes evolved to notice light. Our technology extends that ability even further, and our instincts are deeply tied to the belief that if something truly exists, we should eventually be able to see it or at least measure it in a direct way. Dark matter pushes against that belief. It exists right in the middle of a strange contradiction. We cannot experience it the same way we experience nearly everything else around us, yet it appears to be more common and more powerful than all ordinary glowing matter put together. To understand it, we have to accept that our senses were never designed to reveal the full reality of the cosmos. They were shaped simply to help living creatures survive on a small world filled with forests, storms, oceans, and other forms of life. The universe, it turns out, contains realities far beyond anything biological evolution prepared the human mind to naturally grasp. There's something peaceful about accepting that. You don't need to force the cosmos into becoming simple or familiar. You can instead recognize that reality contains structures and behaviors that refuse to fit comfortably into everyday understanding. Dark matter belongs to that category. It may not expose itself through the methods we prefer, but it reveals itself through the effects that shape the architecture of existence itself. That makes curiosity about dark matter feel less like trying to crack a difficult puzzle and more like learning the rhythm of a silent companion in an invisible dance, where the motions we can see only make sense because of the steady influence hidden beneath them. Another part of the mystery appears once you realize just how enormous the presence of dark matter must be. It doesn't merely gather around galaxies in small pockets. Instead, it surrounds them in gigantic halos, immense invisible spheres stretching far beyond the outer edges of visible starlight. These halos are so vast that if human eyes could perceive them, every galaxy in the sky would appear swollen and expanded, with its bright stars floating inside structures far larger and heavier than the glowing regions alone suggest. Computer simulations reveal something remarkable about this. When dark matter is included, galaxies form naturally and evolve in ways that resemble the universe we observe. Without it, galaxies fail to emerge properly at all. The calculations simply stop making sense without that additional unseen mass. That strongly suggests dark matter is not some minor adjustment added to cosmic equations. It is a dominant ingredient of the universe itself, with gravitational effects stretching across unimaginable distances. Thinking about this can quietly change the feeling of the night sky, not in some dramatic or frightening way, but through a subtle shift in awareness. Instead of imagining stars floating through empty nothingness, you begin to picture them moving through an invisible ocean of something you will never physically touch, something capable of passing through planets, stars, and entire galaxies without slowing, something that exists everywhere, while leaving behind no direct visible sign. Strangely enough, that thought can feel comforting. Rather than living in a universe that is cold and hollow, we begin to see one that is full in ways human senses simply cannot detect. A universe whose deeper structure remains hidden, yet reliable. That reliability is what allows scientists to study the visible universe with confidence, because even if most matter remains unseen, the patterns created by its gravity remain consistent and stable. As we continue drifting deeper into this story, the questions continue unfolding softly and naturally. There's no reason to hurry toward the most difficult details yet, because true understanding begins by recognizing the scale of the mystery itself. Dark matter is not merely a temporary label or a mathematical convenience. It represents the acknowledgement that something real is shaping the cosmos, something humanity still cannot fully explain, something that may one day reveal itself through undiscovered particles or incomplete theories finally brought together. But for now, the most important thing is simply understanding that its influence cannot be denied. And wherever that influence appears, the story of dark matter becomes easier to follow, leading us gradually toward a deeper understanding of how this unseen mass helps hold the universe together. When astronomers first attempted to calculate the amount of mass contained in the universe, they expected those calculations to align with the light they could observe. That assumption seemed perfectly reasonable. If matter exists somewhere, it should produce some kind of detectable signal, whether blazing brightly like a star or glowing faintly like clouds of scattered dust. Early observations were made with this expectation guiding them. Scientists counted galaxies, measured their brightness, studied the gases spread between them, and estimated total mass using only what could actually be seen. At first, the results appeared fairly simple. The visible universe seemed enormous, but still understandable. Everything appeared to follow predictable relationships. But as observations became more precise and more detailed, the numbers began refusing to cooperate. The deeper astronomers looked, the clearer it became that galaxies were staying together with far more gravitational strength than visible matter alone could provide. Something else was exerting additional pull on them adding invisible weight that stars by themselves could never explain. The idea that the universe appeared far heavier than expected was not poetic exaggeration. It was an observational reality. When galaxies rotate, stars near their centers move rapidly, while stars farther away should naturally orbit more slowly, following the same physical principles that govern objects moving around a concentrated central mass. This works much like the way planets travel around the sun in our own solar system. Mercury moves rapidly because it stays close to the sun, while Neptune drifts much more slowly because it lies far away. Gravity controls that relationship, and for planets the pattern is straightforward and predictable. But when astronomers applied that same reasoning to the stars orbiting inside galaxies, something unexpected appeared. The stars near the outer edges were moving far faster than they should have been. Instead of gradually breaking away or being flung into open space, they stayed tightly bound to their galaxies, almost as though an unseen weight was holding everything together, with far greater force than telescopes could account for. This wasn't an isolated irregularity seen only once. The same strange behavior emerged again and again across different galaxies. Everywhere astronomers looked, the imbalance remained. The matter that could actually be seen simply wasn't enough to explain the motions being observed. Scientists repeatedly examined their calculations. They checked the measurements again, refined their instruments, and searched for hidden gas clouds or ordinary material that might explain the missing mass. None of those efforts resolved the issue. The numbers continued pointing toward a much larger quantity of matter than anyone could directly observe. This unseen mass didn't appear to behave like familiar matter. It wasn't gathering into thick regions that blocked light from stars. It wasn't creating glowing nebulae or heating up through collisions. Instead, it seemed to remain quietly distributed in space, affecting motion only through gravity. One simple way to imagine this imbalance is to picture placing several visible objects on a spinning table and noticing that they behave incorrectly. If the table rotates too quickly, the objects should slide outward and fall away. Yet inside galaxies, the stars do not fly off. They remain in place as though some invisible force continuously pulls them inward. Astronomers needed to understand what was causing this effect, and the most direct explanation was that the universe contains far more matter than anyone originally expected. The mismatch revealed by the calculations was not minor. The visible material represented only a small percentage of the total mass required to explain the motions being measured. The unseen matter had to exist in quantities several times greater than ordinary visible matter. As more evidence continued to accumulate, scientists adopted the term dark matter as a label for this invisible component. The phrase was never intended to sound mysterious or dramatic. It simply described matter that does not interact with light. That was the only conclusion researchers could confidently make at the time. The heavier the universe appeared through these observations, the clearer it became that dark matter was not some occasional feature scattered here and there. It appeared to be the dominant form of matter throughout the cosmos. If someone could somehow place the entire universe on a scale, the visible material would account for only a small fraction of the total weight. Everything else would come from something that neither emits, absorbs, nor reflects light in any detectable way. This realization completely changed how astronomers understood the formation of galaxies and the behavior of the universe on enormous scales. The thought that most of the universe's mass is invisible may sound difficult to accept at first, but the reasoning behind it follows ordinary physical principles. Gravity reliably reveals the presence of mass. If stars and galaxies move too quickly to remain bound by the gravity of visible matter alone, then additional unseen mass must be contributing to the gravitational pull. And if those systems continue holding together instead of falling apart, the hidden mass must be extremely large. That was the reality astronomers encountered. They were not inventing strange fantasies or abandoning known physics. They were applying the exact same gravitational rules that explain falling apples and planets orbiting the Sunday. When the equations failed to balance, the existence of missing mass stopped being optional and became necessary. Additional clues emerged from studies of galaxy clusters. These enormous groups of galaxies behave like giant families connected through gravity across vast regions of space. Back in the 1930s, astronomers measured the speeds of galaxies inside these clusters and discovered that they were moving far too quickly to remain gravitationally bound by the visible matter alone. This created early suspicion that something important was missing, although the scientific tools available at the time were still limited. Many decades later, improved instruments and more precise observations brought researchers back to the same conclusion with far greater certainty. Galaxy clusters required much more mass than what telescopes could directly see. Without that additional mass, the clusters should have drifted apart long ago. Instead, they remained together, suggesting that a large gravitational influence from something invisible was holding them in place. Light itself eventually provided another important clue. When light from extremely distant galaxies travels through massive clusters, gravity bends that light along its path, an effect known as gravitational lensing. Scientists can measure how strongly the light bends and calculate the amount of mass needed to create that distortion. When those calculations were performed, they repeatedly revealed far more mass than the visible matter could provide. This separate method strongly supported the earlier discoveries. It did not depend on observing the motion of stars or galaxies at all. It relied entirely on how gravity altered the path of light itself. Once again, the amount of mass inferred from the observations was far greater than anything visible in space. Together, these discrepancies pointed toward a much larger, hidden structure underlying reality, where the visible universe may only represent a thin outer layer resting upon a far deeper and heavier invisible foundation. This hidden weight didn't merely hold galaxies together. It influenced the way they emerged during the earliest stages of cosmic evolution. Computer simulations made this increasingly obvious. Whenever scientists built models using only ordinary visible matter, galaxies had difficulty forming in a natural and stable way. The final arrangements failed to resemble what astronomers actually observed through telescopes. But once those same simulations included an underlying presence of dark matter, galaxies began forming into organized and familiar structures. The invisible mass acted like a framework, guiding visible material into the shapes we now recognize across the universe. This was not some small adjustment or secondary feature. It was absolutely necessary. Without that unseen mass, the cosmos would look completely different from the universe surrounding us now. Stars would not gather in the same arrangements. Massive cosmic structures would fail to create the enormous web-like patterns revealed by modern astronomical surveys. Gradually, researchers realized that the universe is not simply a little heavier than expected. It truly contains far more mass than visible matter alone can explain. Everything we can directly observe represents only a tiny portion of a much greater whole. The consequences of this idea extend through every area of cosmology. The speed at which galaxies collide and merge, the arrangement of galaxy clusters, the leftover radiation from the early universe, all consistently point toward a cosmos shaped by mass that does not interact with light. This hidden component quietly affects everything while remaining beyond normal detection. It passes through planets, stars, and even through us without friction or resistance. It doesn't heat up from impacts or cool down after collisions the way ordinary matter does. It simply remains present, continuously exerting gravitational influence. The discovery that the universe contains vastly more mass than anticipated immediately raised deeper questions. What exactly is this invisible substance? Why does it behave so differently from familiar matter? Is it made from unknown particles? Could it result from changes to the laws of physics themselves? At first, there were no clear answers, but the mystery offered scientists a path forward. The beginning was simply accepting the scale of what the evidence showed. Before proposing strange theories or exotic possibilities, the measurements themselves had to be acknowledged. And those measurements demonstrated very clearly that the visible contents of the universe are nowhere near enough to explain its gravitational behavior. Something additional exists. This conflict between what we can observe and what gravity requires cannot be solved by making tiny adjustments to existing equations. The discrepancy is far too enormous. The extra mass necessary to explain the observations is not a minor addition, It exceeds the total visible mass by several times. That is why the concept of dark matter became so important. It was not created as an arbitrary invention or an attempt to force a new substance into science without evidence. It emerged because the universe stubbornly refuses to behave as though visible matter is all that exists. When viewed this way, the idea that the universe is unexpectedly heavy stops sounding surprising and instead becomes the starting point for understanding cosmic reality. The imbalance in mass is not a mistake hidden in the data. It is a clue pointing toward the actual composition of the cosmos. Once researchers accepted that most of the universe is invisible, they could begin exploring the possible forms this hidden matter might take. Even though many details remain uncertain, the larger pattern stays remarkably consistent. The gravitational effects appear everywhere scientists are able to measure them. They appear inside galaxies, among galaxy clusters, in the bending of light across space, in the temperature fluctuations of the cosmic microwave background, and in simulations designed to reconstruct the universe on its largest scales. Every time astronomers use a new technique to measure the universe's mass, they arrive at the same conclusion. The visible material never produces enough gravity to explain what is observed. No matter how many stars are counted, or how carefully clouds of dust are analyzed, the requirement for additional mass always returns. This agreement across many independent forms of evidence greatly strengthens the argument that dark matter is not imaginary, but an authentic component of reality. The fact that we cannot see it does not make it less significant. Some aspects of the universe shape events through interactions that human senses cannot directly detect, and dark matter appears to belong to that category. The recognition that the universe carries far more hidden weight than expected also changes the way we think about the environment surrounding Earth. Rather than drifting through emptiness, our planet moves through regions filled with invisible matter. This does not suggest danger, nor does it mean dark matter noticeably affects daily life. It simply reveals that reality is more complicated than human senses alone can perceive. The gravitational structure of the cosmos is shaped by both visible and invisible matter together, and the movement of stars and galaxies reflects the combined effect of both. Once scientists realized that unseen mass was contributing so heavily to the universe, it naturally led them to examine how this hidden matter influences the structures we can actually observe. When galaxies were first analyzed in detail, they did not behave like simple mechanical systems at all. Instead, they behaved as though something unseen was surrounding them and keeping them bound together more powerfully than the visible stars alone ever could. It seemed as though every galaxy was wrapped inside an invisible layer, a hidden structure pulling the outer stars inward with a force that should not have existed if only visible matter were present. Scientists did not casually describe this behavior as a kind of glue. The idea emerged from repeated observations and measurements that consistently refused to match what existing expectations predicted. A galaxy is not a solid object spinning as one piece. It is a vast collection of stars, gas, dust, and other visible substances, all moving under the influence of gravity. Certain regions rotate faster than others, yet the overall motion should still follow the same gravitational principles seen elsewhere in nature. When the observations failed to match those expectations, researchers were left asking what exactly was missing. If stars were traveling too fast to remain held together by the visible mass alone, then another source of mass had to exist. Otherwise, those stars should slowly escape outward, and galaxies would eventually fall apart over cosmic periods of time. But galaxies do survive. They remain remarkably stable across billions of years. That meant the missing stabilizing influence could not be minor or insignificant. It needed to account for an enormous amount of mass. As more observations accumulated, astronomers began forming the picture of galaxies surrounded by gigantic halos made of unseen matter. These halos emitted no light and could not be captured directly in ordinary optical images, yet their existence could be inferred through the effects they produced on motion. When scientists created models of galactic behavior, they discovered the visible part of a galaxy functioned more like a bright, inner region sitting inside a much larger reservoir of hidden mass. The halo stretched far beyond the last visible stars, continuing outward into darkness without any obvious edge. The stars orbiting near the outskirts of galaxies were not being held in place by visible material alone. They were being controlled by this enormous invisible halo that contributed most of the galaxy's total mass. This invisible glue was not glue in the ordinary physical sense. It did not bind through friction, contact, or stickiness. Its influence operated entirely through gravity. Anything with mass can attract other things with mass. And if enough unseen mass exists, it can create an extremely powerful gravitational field, even while remaining completely invisible. That was exactly what dark matter appeared to be doing. It did not reflect or scatter light, nor did it gather into glowing structures, but it shaped the gravitational environment of the entire galaxy. Stars moved according to that hidden gravitational landscape, following paths determined by matter they could neither collide with nor directly interact with. That made dark matter a very unusual form of cosmic glue, capable of holding galaxies together without touching them the way ordinary matter would. The reality of these halos became even more convincing when astronomers examined many different types of galaxies. Large spiral galaxies, like our own displayed rotation curves that stayed flat rather than decreasing farther from the center. Smaller galaxies revealed similar behavior, in some cases even more dramatically. Certain dwarf galaxies contained so little visible matter that they should not have remained intact at all if dark matter did not exist. Yet they continued to survive. They did not scatter apart. They rotated with an unexpected level of stability. The simplest explanation was that dark matter supplied most of the gravitational attraction within them, and this pattern appeared repeatedly across many different galactic systems, not just in a handful of unusual examples. Additional support for this invisible glue came from gravitational lensing. When light from extremely distant objects travels close to a galaxy, the galaxy's gravity bends the path of that light. By calculating the amount of bending, astronomers can estimate how much mass must be present. Again and again, the distortion was far stronger than visible matter alone could explain. Galaxies turned out to contain much more mass than their visible appearance suggested. Their gravitational reach extended well beyond what telescopes could directly observe, once more pointing toward the existence of dark matter halos. These halos were not merely large additions to galaxies, they dominated the overall mass distribution almost completely. The visible stars and glowing regions existed inside them, like small illuminated islands, buried within gigantic invisible structures. The idea of dark matter acting like glue became even more meaningful when scientists observed galaxies colliding with one another. During such collisions, stars almost never strike each other directly, but enormous gas clouds do collide. The gas slows down, heats intensely, and can create massive shock waves. Yet, gravitational lensing revealed something remarkable. Most of the total mass involved in those collisions passed straight through without slowing at all. The majority of the mass did not remain where the gas accumulated. Instead, it stayed aligned with the stars, something that should not have happened if the extra mass was simply hidden within the gas itself. This strongly suggested that the unseen mass did not interact significantly with gas, nor even with itself, in ways that would create friction or resistance. It moved through the collision almost untouched, continuing to exert gravitational influence without actively participating in the violent interaction. That behavior implied dark matter was not only invisible, but also almost completely non-reactive except through gravity. This strange picture became even clearer through observations of a system called the Bullet Cluster. Two massive galaxy clusters had crashed into one another, and the hot gas within each cluster interacted intensely, slowing down and heating up during the collision. Yet when astronomers examined the gravitational lensing effect, they discovered that most of the total mass had continued forward, almost untouched, separating itself from the visible gas clouds. That observation matched the predictions of the dark matter model remarkably well. The unseen component neither slammed into itself nor compressed during the impact. Instead, it passed directly through while still maintaining its gravitational pull on everything around it. This became powerful evidence that the invisible substance helping galaxies remain bound together was not simply ordinary matter hiding in darkness. Whatever it was, it possessed characteristics that suggested it belonged to something fundamentally different from the matter we already understood. Realizing the importance of this invisible binding material changed the way scientists thought about galaxy formation. Before the idea of dark matter gained widespread acceptance, accurately modeling the growth of galaxies proved extremely challenging. If the young universe had contained only visible matter, the clumps of gas would not have gathered rapidly enough to create galaxies within the amount of time available after the Big Bang. The structures astronomers observed required additional gravity, and dark matter supplied that missing influence. Computer simulations demonstrated that once dark matter was included, dense concentrations began forming very early in cosmic history. These concentrations became the foundations around which ordinary gas collected. Over millions of years, that gas gradually cooled, stars ignited, and galaxies emerged into the forms we observe today. Without those dark matter foundations, the large-scale structure of the universe would look completely different from what telescopes actually reveal. Describing dark matter as an invisible glue is a useful way to understand its stabilizing role inside galaxies. Still, it's equally important to remember that this glue behaves unlike anything familiar in everyday life. It does not gather into compact objects the same way visible matter can. Rather than forming dense clumps, it spreads into wide, smooth halos surrounding galaxies. It does not flatten into rotating disks, it does not collapse inward to create stars. Its role is to stop galaxies from flying apart while remaining absent from the visible details we normally associate with them. It provides the underlying framework, instead of shaping the luminous features directly. This division of responsibilities is unusual. Ordinary matter creates the glowing structures we see through telescopes, while dark matter controls much of the gravitational stability holding everything together. This glue-like effect also becomes clear inside galaxy clusters, where dark matter serves as the primary binding force. These clusters are unimaginably large systems containing hundreds or even thousands of galaxies gathered together. Compared with the enormous mass supplied by dark matter, the visible matter almost seems secondary, like decoration layered onto a deeper structure. The galaxies orbit around the cluster's center because of a gravitational field shaped mainly by material that cannot be seen directly. Without dark matter, these giant clusters would not stay connected over time. They would gradually spread outward and fall apart. Instead, they remain gravitationally bound, once again pointing toward the existence of something invisible, holding them together beyond what ordinary matter alone could explain. As astronomers uncovered more about this unseen cosmic glue, new questions continued to appear regarding its true identity. Knowing that it helped bind galaxies together was no longer enough. Scientists wanted to understand what it actually consisted of. Many possibilities were proposed, from entirely new particles never before detected to theories suggesting gravity itself might behave differently on enormous scales. But before any alternative ideas could replace the dark matter explanation, the observational evidence had to remain consistent. Over time, repeated measurements kept showing that the simplest interpretation continued to fit the data best. Something invisible was exerting gravitational influence in ways that ordinary visible matter simply could not account for. The effects of this hidden glue also appeared when researchers studied the motion of stars inside spherical systems. Unlike spiral galaxies, these systems lack clear rotating arms or bright, organized structures. They appear much more spread out and diffuse. Yet the stars inside them still moved as though surrounded by an enormous amount of unseen mass. The farther astronomers looked from the center, the more necessary dark matter became to explain the motions they observed. These behaviors were not chaotic or accidental. They followed regular patterns that matched the presence of mass extending far beyond the visible edges of the galaxies themselves. Beyond this, the existence of invisible glue also explained how some extremely faint galaxies could survive without falling apart. Ultra-diffuse galaxies contain very small numbers of stars, making them incredibly difficult to detect against the darkness of space. Yet the stars they do contain move as though embedded inside gigantic halos of dark matter. If those visible stars represented all the mass present, these galaxies would not possess enough gravity to stay intact. But they continue to exist as stable systems. This became another important piece of evidence supporting the idea that dark matter plays a major stabilizing role throughout the universe. Across all of these observations, the same conclusion repeatedly emerges. Galaxies are not held together only by the matter human beings can see. Their stability depends heavily on a vast unseen component surrounding them. This understanding did not arrive through one sudden discovery. Instead, it emerged slowly through decades of accumulating evidence, all pointing consistently toward the same explanation. Even now, despite how persuasive the evidence has become, curiosity remains about the true nature of this invisible glue. Researchers still do not possess a final answer regarding what dark matter actually is, yet the repeated consistency of the gravitational evidence remains extremely difficult to dismiss. When reflecting on all these discoveries, the universe starts to feel less like a place shaped mainly by visible objects and more like a structure governed largely by hidden forces. The stars create the glowing patterns we admire in the night sky, but the paths they follow are guided by an enormous background of invisible mass surrounding everything. The glue never calls attention to itself. It does not glow, it does not produce sound, and it offers no visible signal announcing its presence. It simply creates the gravitational framework that allows galaxies to hold together in the forms we observe today. The awareness that the universe might be missing something essential did not begin with sophisticated computers or modern simulations. It started with simple observations made many years before dark matter became a familiar scientific concept. The first astronomers studying the movement of galaxies and galaxy clusters were not trying to uncover hidden mass. They were only attempting to understand how objects traveled through space. They expected those motions to obey the known laws of gravity, and when the observations refused to align with those expectations, the situation became increasingly strange in ways that could not easily be explained away as ordinary error. These early hints did not immediately suggest the existence of a completely new type of matter. At first, they appeared as subtle inconsistencies, small signs that the numbers were failing to balance correctly. One of the earliest pieces of evidence emerged during the 1930s through the study of galaxy clusters. Back then, calculating distances and velocities was extremely challenging, and the available instruments were far less accurate than the technology astronomers use now. Even with those limitations, the motions of galaxies inside certain clusters raised difficult questions. A Swiss astronomer examining these systems tried to estimate the total amount of mass by studying how quickly the galaxies were moving. His logic was straightforward. If galaxies inside a cluster travel at high speeds, then the cluster itself must contain enough mass to keep everything gravitationally connected. Otherwise, over long periods of time, the galaxies would simply drift apart. But when he completed the calculations, the amount of mass required to hold the cluster together was far greater than the mass visible through telescopes. The difference was not minor. It exceeded expectations by several times. At first, the scientific community did not fully accept the conclusion. Many researchers considered the result unusual and possibly caused by inaccurate measurements. Early instruments had serious limitations, and distance estimates during that period could easily contain large errors. The suggestion that enormous quantities of invisible matter filled the universe sounded highly speculative at the time. Many scientists assumed that once observations improved, the discrepancy would eventually disappear and align with visible matter alone. For a period, that explanation seemed sensible enough. Astronomers continued collecting more detailed data, expecting the mismatch to shrink as technology advanced. Yet the inconsistency remained. It appeared again when researchers studied how galaxies rotated. These investigations accelerated decades later. Once improved instruments allowed scientists to measure the movement of stars orbiting around galactic centers with greater precision. What they found created another major puzzle. Stars located far from the centers of galaxies were moving much faster than expected. According to traditional gravitational theory, those distant outer stars should have been traveling more slowly. The visible material concentrated near the galactic center was nowhere near enough to keep them bound in stable motion. If galaxies only contained the stars and gas astronomers could see, the systems should have become unstable and gradually torn apart. Yet the galaxies stayed intact, with stars continuing to follow steady orbits that should not have been possible based solely on visible matter. This was not an isolated or fringe result. The same pattern appeared repeatedly across numerous galaxies. Spiral galaxies especially displayed rotation curves that stayed relatively flat instead of declining with increasing distance from the center. As astronomers gathered larger amounts of observational data, the pattern kept repeating itself. The outer regions of galaxies behaved as though they were immersed inside a vast halo of invisible mass. This understanding did not arise from one single observation. It developed slowly through an expanding collection of evidence that stubbornly refused to match the expected gravitational behavior. Eventually, the discrepancy became impossible to comfortably ignore. Even if the early measurements of galaxy clusters contained uncertainties, the galactic rotation curves were far too consistent and too clear to dismiss casually. As scientists kept comparing the predicted motions of galaxies with the motions they actually observed, they were forced to consider possibilities extending beyond ordinary miscalculations. The mismatch continued appearing in different situations. Measurements based on visible light could not explain the required amount of mass. Infrared observations also failed to uncover enough hidden ordinary matter to solve the problem. Scientists explored explanations involving faint stars, thick clouds of gas, or other difficult-to-detect forms of normal matter, but none of those possibilities provided enough mass to stabilize galaxies and clusters. The more carefully astronomers searched, the clearer it became that ordinary matter by itself could not account for the structure of the universe. Beyond galaxy rotation curves and cluster dynamics, additional evidence slowly emerged from other directions. When astronomers used gravitational lensing to map the distribution of mass inside galaxy clusters, they discovered that the bending of light revealed much more mass than luminous matter alone could explain. This lensing effect did not depend on how brightly objects shone, but instead on how strongly mass warped the path of light traveling from distant background galaxies. Because the amount of bending depends directly on how much total mass is present, gravitational lensing maps became another independent method for measuring cosmic structures. Again and again, those maps revealed concentrations of mass that failed to match the locations of visible matter. Over time, it became increasingly difficult to believe that all this hidden mass could simply consist of ordinary objects that somehow escaped observation. Looking even farther back into the early universe, scientists also found unusual evidence within the temperature fluctuations of the cosmic microwave background. When researchers carefully measured the faint irregularities contained in this ancient radiation, they uncovered patterns connected to the density differences that existed shortly after the universe first formed. Those variations preserved a record of how matter had been distributed during that distant period. Detailed analysis demonstrated that ordinary visible matter alone could not create the observed patterns. The cosmos appeared to contain a large quantity of mass that did not interact with radiation, once again suggesting the existence of something beyond familiar matter. As evidence continued emerging from multiple observational techniques, the overall picture became harder to ignore. The unseen mass was not a minor ingredient within the universe. It represented most of the universe's total matter content. What made this conclusion especially compelling was that it arose from separate and unrelated lines of investigation, each supporting the others independently. No matter which method scientists used to weigh the universe, gravity repeatedly pointed toward the existence of an invisible component. This growing understanding did not immediately resolve the mystery, but it established the necessity of searching for something that possessed mass without interacting with light. The idea of dark matter emerged from this realization, not as a random assumption, but as the most necessary explanation capable of accounting for many different observations at once. The first researchers who encountered these inconsistencies did not instantly announce the discovery of a completely new kind of matter. Instead, they explored possibilities carefully, tested competing ideas, and slowly eliminated explanations that failed to match the evidence. Whatever the missing component was, it needed to contribute gravitational effects without participating in electromagnetic interactions. That requirement ruled out most known forms of matter. It meant this hidden substance would neither emit light nor absorb or reflect it. It would not create luminous structures, would not collapse into stars, and would remain invisible through ordinary observational methods. The only dependable sign of its existence would come from its gravitational influence. This realization transformed how scientists approached the study of the universe. Rather than depending entirely on visible objects, astronomers began following cosmic motions and behaviors in order to uncover what could not be observed directly. Movement became a method for detecting hidden mass. The bending of light evolved into a tool for mapping invisible structures. Temperature fluctuations in the cosmic microwave background became evidence, revealing how mass had been distributed in the young universe. Every approach led toward the same conclusion. Something essential was absent from the visible inventory, and whatever it was, it controlled most of the universe's mass budget. This change in perspective did not happen overnight. It emerged gradually as repeated efforts to explain observed motion using visible matter alone continued to fail. Scientists eventually had to accept that the universe could not be described accurately by light alone. That realization implied that even the most advanced telescopes would reveal only part of reality. Instruments capable of measuring mass indirectly became just as valuable as those designed to capture images of visible objects. As the concept gained wider acceptance, theoretical physicists began considering what forms this unseen matter might possess. They explored models describing matter that carried mass, while lacking electromagnetic interactions. These ideas did not immediately solve the mystery, but they opened entirely new directions for research. Discovering what was missing required both theoretical models and observational evidence, with each continually guiding the other. The effort was never about proving one preferred explanation from the start. Instead, it involved ruling out alternatives that could not simultaneously account for galaxy rotation, galaxy cluster dynamics, gravitational lensing observations, and patterns within the cosmic microwave background. While scientists continued developing the realization that something major was absent, attempts to explain the missing mass using ordinary matter eventually reached a dead end. Astronomers searched for large populations of dim stars, isolated planets, and cold clouds of gas. At first, these possibilities seemed reasonable because faint objects can naturally be difficult to detect. But as observational surveys expanded across broader wavelength ranges, these hidden ordinary objects failed to appear in sufficient numbers. They could not explain even a modest fraction of the missing mass, much less most of it. The invisible component clearly had to differ from ordinary matter in a fundamental way. The idea that most of the universe's mass might be invisible challenged long-standing assumptions about matter itself. It suggested that the familiar matter humans interact with every day is not the primary substance shaping the cosmos. Instead, the dominant form of matter may belong to something entirely different from anything commonly experienced or directly observed. This redirected scientific attention away from simply listing visible cosmic structures and toward understanding the role invisible mass plays in shaping the evolution of the universe itself. The discovery that something appeared to be absent therefore became the foundation for a far broader scientific pursuit, one that would continue through investigations into cosmic structure formation, particle physics, and the study of cosmology. Naming this unseen substance dark matter was never intended as a final explanation. The phrase functioned more like a temporary label for a mystery that clearly required deeper investigation. The name only indicated that this matter did not interact with light in any observable way. As observations accumulated over time, the usefulness of that placeholder became increasingly important. The evidence continued pointing toward a universe organized by a component that stubbornly refused to reveal itself directly, while still exposing its existence through gravity. Slowly, researchers shifted from asking whether something might be absent to accepting that the universe itself could not be properly explained without including this invisible ingredient. The divide between what observations showed and what theories predicted became too significant to dismiss any longer. Realizing that something was missing did not resolve the mystery. Instead, it marked the beginning of trying to understand why this hidden mass existed at all, and how it influenced everything from individual galaxies to the largest arrangements of matter in the cosmos. When astronomers first started carefully examining the movement of stars inside galaxies, they expected the results to follow familiar gravitational rules. Stellar motion should have obeyed the same principles observed everywhere else gravity operates. Greater mass produces a stronger pull. Greater distance weakens that pull. These concepts were dependable, supported by centuries of evidence and calculation. Because of that, the first measurements of stellar motion inside galaxies were expected to reinforce existing understanding. Instead, the data uncovered a discrepancy so large that it forced scientists to rethink some of their most basic assumptions. The stars were not moving the way they should have if visible matter alone were controlling them. Their motion implied the existence of an unseen source of mass, something providing extra gravitational force that kept galaxies bound together more tightly than expected. When a star circles the center of a galaxy, its speed depends on the total amount of mass located within the boundaries of its orbit. Stars positioned near the galactic center contain a large amount of visible matter inside their orbital path. Naturally, they travel faster, which matches predictions. Stars farther away from the center contain far less visible mass within their orbits. They should therefore move more slowly, much like the planets farther from the Sun orbit more slowly than the planets nearby. At first glance, these expectations appeared completely reasonable. Yet when astronomers carefully measured stellar velocities at different distances from galactic centers, the results refused to align with those predictions. The stars located in the outer regions were not slowing down as expected. Many of them were moving at nearly the same speed as stars much closer to the center. This behavior contradicted the gravitational influence that visible matter alone should have produced. The mystery became even more compelling as additional observations were gathered. Researchers found the same strange pattern almost everywhere they looked. No matter which galaxy they studied, the outer stars continued moving with an unexpected stability, often at velocities high enough that they should have escaped into intergalactic space entirely. Yet they remained trapped in orbit, circling their galaxies as though held in place by something massive and invisible. This indicated that the mass responsible for stabilizing galaxies was not concentrated only in bright, visible regions. Instead, it appeared to extend far beyond the glowing stars, surrounding galaxies within enormous halos of unseen matter. The stars were clearly reacting to gravity, but most of the source creating that gravity could not be seen directly. To understand why this discovery was so surprising, it helps to compare it with the behavior of our solar system. The Sun contains almost all of the solar system's mass. Planetary motion depends primarily on the Sun's gravitational influence. The farther a planet is from the Sun, the weaker that pull becomes, and the slower the planet moves in its orbit. This pattern is predictable and perfectly consistent with observations. If the planet suddenly started traveling much faster than the Sun's mass could explain, scientists would immediately conclude that some additional hidden influence must be involved. That is essentially what astronomers found when studying galaxies. The stars behaved as though most of the mass was not concentrated in the center at all, but spread throughout a huge invisible halo surrounding the galaxy. At first, some astronomers suspected that the amount of visible matter had simply been miscalculated. Perhaps there were enormous populations of dim stars, too faint to detect easily, or vast clouds of cold gas emitting almost no light. Maybe thick dust clouds were obscuring large portions of galaxies from observation. These possibilities were sensible enough to investigate, but none of them solved the problem. Even after including hidden gas, faint stars, and obscuring dust in the calculations, the numbers still fell far short of explaining the observed motions of the stars. The amount of mass required was far beyond anything ordinary visible matter could provide. The stars located near the outer regions of galaxies kept orbiting at speeds far too high to be explained by the gravity of visible material alone. As more observations accumulated, Astronomers gradually became convinced that galaxies were surrounded by enormous halos made of unseen substance. These halos never appeared in photographs or telescope images because they did not interact with light in any detectable way. The stars near the galactic edges were moving rapidly, not because gravity itself was flawed, but because they were responding to a gravitational pull created by this hidden mass. The more researchers examined galactic rotation curves, the harder it became to deny that most of a galaxy's mass could not actually be seen. Through their endless orbits, the stars quietly revealed this truth, movement after movement, demonstrating that galaxies could not maintain stable structures without a major invisible component surrounding them. What made the evidence especially convincing was how consistently the same pattern appeared. Spiral galaxies displayed the effect clearly through their flattened rotation curves. Elliptical galaxies were more difficult to study in detail, yet they also suggested the presence of enormous amounts of unseen matter. Dwarf galaxies provided an even more dramatic example. Some contained only a small number of visible stars, but those stars still traveled fast enough to imply the existence of halos vastly heavier than the luminous material inside them. This suggested that dark matter was not some rare characteristic found only in unusual galaxies. It seemed to be universal, appearing everywhere astronomers could make gravitational measurements. Another fascinating clue emerged when scientists compared the visible arrangement of galaxies to the distribution of their total mass. In many situations, the visible matter simply was not organized in a way capable of producing the gravitational effects being observed. If all the mass existed only in the bright central areas, then stars farther away should gradually slow down as their distance increased. But that did not happen. The gravitational influence clearly extended far beyond the luminous regions, wrapping around the galaxy like an enormous invisible shell. This hidden structure controlled stellar motion in a way that could not be reproduced simply by rearranging the visible matter. No matter how astronomers adjusted the light distribution or refined their calculations, the same result continued appearing. The stars at the outer edges were not merely traveling too quickly. Their movements specifically suggested that the unseen mass followed a particular large-scale arrangement. The simplest interpretation was that this invisible matter formed a roughly spherical halo surrounding the galaxy. Unlike visible matter, it did not collapse into a flat rotating disk. It did not condense into stars, planets, or glowing clouds. Instead, it remained widely distributed, stretching far beyond the regions that emitted light. The galaxies we see appeared to exist inside a much larger gravitational structure. The stars responded to that structure, not only to the visible material around them. An analogy can help make this easier to picture, even though the real physics involved is much more complicated. Imagine a small glowing object suspended inside a gigantic dark sphere. If the sphere contains enough mass, everything moving within it will react to that mass, despite the sphere itself remaining completely invisible. The illuminated object may appear to be the only thing present, but the motions occurring inside would eventually expose the existence of the hidden sphere. Galaxies behave in a similar way. The movement of their stars reveals the presence of the surrounding halo. The halo itself cannot be seen directly in images, but its gravitational influence becomes impossible to ignore. As this understanding strengthened, astronomers began adding dark matter into computer simulations designed to model galaxy formation. Whenever simulations included only visible matter, the resulting galaxies failed to resemble the ones observed through telescopes. They ended up too small, too unstable, and lacking the broad, extended structures visible throughout the universe. But when massive dark matter halos were included, galaxies formed in ways that looked much more realistic. They developed stable shapes, maintained their structure over time, and produced rotation patterns closely matching actual observations. This indicated that dark matter was not merely an invented solution created to patch an observational problem. It appeared to be essential for explaining how galaxies form, evolve, and remain stable across cosmic timescales. The mystery became even deeper as scientists tried to determine the true nature of dark matter itself. Yet long before discussions about exotic particles or competing theories began, the stars had already provided the crucial clue. They were moving far too rapidly to be held together by visible matter alone. Their motions were measured again and again across different galaxies, with different telescopes, different instruments, and under different observational conditions. The outcome remained remarkably consistent. The stars were not behaving strangely or incorrectly. They were behaving exactly as expected if most of a galaxy's mass existed in invisible form. What they quietly revealed was that the universe contained far more material than humanity had ever imagined. One particularly dramatic example of this phenomenon appeared in galaxies called low-surface brightness galaxies. These galaxies emit very little visible light, yet the stars inside them still move at speeds comparable to those found in galaxies that shine much more brightly. That shouldn't happen if ordinary matter were the only source contributing to gravity. These galaxies should almost fall apart instead of remaining stable. But their rotation curves stayed remarkably flat, revealing that some strong gravitational influence was holding them together even though it could not be seen in the dim glow of stars. This became another powerful indication that something important was missing from the visible picture. The hidden mass clearly wasn't connected to how bright a galaxy appeared. A galaxy could shine brilliantly or remain extremely faint, yet still be surrounded and controlled by a massive dark halo. Observations of galactic gas introduced even more evidence. Gas clouds often stretch much farther outward than the visible stars, and by measuring the movement of this gas, astronomers were able to trace the gravitational field to much greater distances. The same strange pattern kept appearing. Even in areas containing very few stars, or sometimes none at all, the gas still traveled at speeds that demanded the presence of additional unseen mass. These observations strengthened the conclusion that dark matter halos existed almost everywhere, and that they controlled motions far beyond the visible boundaries of galaxies. Another important clue emerged when astronomers compared different kinds of galaxies. Some galaxies possess dense and bright central bulges, while others appear much more spread out and diffuse. Even with these structural differences, their rotation curves frequently displayed the same flattening pattern. That consistency suggested the invisible mass was not connected to the glowing structure itself. Instead, it wrapped around the entire galaxy independently of the exact arrangement of stars. The stars were simply responding to a deeper gravitational framework generated by the surrounding halo. The quiet mystery carried by the stars extended far beyond single galaxies. When astronomers studied entire galaxy groups and clusters, they discovered that these enormous systems also moved in ways requiring huge quantities of unseen matter. The galaxies were bound together far more tightly than visible material alone could explain. Their motions revealed the existence of a much deeper gravitational well underneath. This showed that dark matter did not exist only inside individual galaxies, but also across vastly larger cosmic scales. Through their orbits, stars provided some of the clearest evidence that a major piece of the universe was absent from the visible matter inventory. Without directly interacting with anything unusual, they still exposed the structure of the gravitational environment surrounding them. Their motion became a natural measuring tool, sensitive to how mass was distributed nearby, and because stars move predictably under gravity, astronomers could trust the speeds being observed. These motions were not random fluctuations. The stars followed stable orbital paths that accurately reflected the total mass contained within the galaxy. Even when scientists examined galaxies from different periods in cosmic history, the same behavior continued to appear. Young galaxies forming in the early universe already displayed rapid rotation and mass distributions that pointed toward the existence of dark matter. This suggested that dark matter had been shaping the universe since extremely early times, influencing how galaxies developed long before they fully matured. The stars were already embedded inside much larger invisible structures before the universe evolved into its current form. As the amount of observational evidence expanded, it became increasingly obvious that dark matter was not some tiny correction added to improve theoretical models. It was essential for explaining why stars moved the way they did. Stellar motions became clues scattered throughout the sky, all pointing toward a universe whose structure depended heavily on something unseen. These clues were not uncertain or vague. They were measurable, repeatable, and remarkably consistent. Evidence came from giant galaxies and dwarf galaxies, from nearby systems and extremely distant ones, from clouds of gas and dense star clusters alike. Every independent observation supported the same overall conclusion. As more measurements accumulated, astronomers did not simply stare at the mystery in confusion. They continued using stellar motion to construct maps of the invisible halos, gradually creating clearer models of how dark matter might be spread throughout galaxies. Those maps revealed structures extending enormously far beyond the regions where visible stars existed. They showed variations in density within the unseen mass, demonstrated how the halo supported the galaxy, and explained how it shaped the motions occurring inside it. The stars never revealed exactly what dark matter truly is, but they made it impossible to dismiss its existence. The deeper astronomers investigated these strange stellar motions, the clearer it became that gravity alone, at least gravity generated solely by visible matter, could not fully explain the behavior of the universe. Gravity itself was acting exactly the way physics predicted, yet the results failed to match the amount of observable matter present. This did not mean gravity was broken or malfunctioning. It meant gravity was reacting to something additional, something missing from the visible accounting. Slowly, astronomers realized that gravity appeared to have a hidden companion contributing to the total pull, one that could not be observed directly, one that emitted no light and produced no sound, yet still guided the motion of galaxies with extraordinary consistency. This invisible companion was understood only through the effects it created, rather than through direct contact, and uncovering its true nature became one of the most important goals in modern astronomy. Whenever an object travels under the effect of gravity, its motion reveals information about the amount of mass influencing it. This principle has proven dependable in countless situations. It shaped the earliest studies of planetary motion and helped scientists determine how stars and galaxies were expected to move. If gravity appeared stronger than predictions allowed, then some additional source of mass had to be responsible for that stronger pull. If systems remained gravitationally connected when they should have drifted apart, then unseen mass needed to exist somewhere within them. These conclusions were not based on guesswork. They came directly from the same gravitational laws that explain why objects fall on Earth. Stars, galaxies, and galaxy clusters were not violating those laws. They were obeying them with remarkable precision. That meant the problem was not that gravity itself had failed, but that something invisible was contributing additional mass. This hidden influence became even more obvious when astronomers compared the visible matter inside galaxies with the amount of gravity necessary to keep those galaxies intact. The discrepancy was enormous. The material we could actually see represented only a small portion of the total mass required. Stars at the outer edges of galaxies moved at speeds that demanded far more mass than visible matter could provide, and even regions closer to the center displayed gravitational behavior inconsistent with estimates based only on emitted light. When scientists extended these calculations to much larger cosmic systems, the mismatch became even greater. Galaxy clusters required tremendous quantities of mass to prevent their member galaxies from escaping. Without an unseen contribution, those clusters should have broken apart billions of years ago. Yet they remained stable, moving in ways that revealed gravitational fields vastly stronger than anything visible alone could create. These observations suggested a hidden companion to gravity, though companion in this case referred to something participating in gravity rather than changing gravity's underlying nature. Gravity responds to mass, and the unexplained pull implied that most of the mass itself was invisible. That unseen mass created the additional gravitational strength. It did not rewrite gravity's laws. It altered the amount of material gravity could act upon. This distinction became central to how astronomers approached the mystery. The basic laws of physics remained intact, What was incomplete was the inventory of matter in the universe. This hidden partner was not a newly discovered fundamental force. It was simply mass that gravity reacted to, exactly as it always had. Confidence in this interpretation grew stronger when gravitational lensing exposed mass patterns inside distant galaxy clusters. Since massive objects bend light, astronomers could use distorted light paths to map mass independently from visible brightness. But when these lensing maps were compared with ordinary optical images, the two failed to align. The strongest regions of light bending often appeared far from the brightest visible objects. The overall mass distribution spread wider and carried much more weight than luminous matter alone suggested. This strengthened the idea that gravity was responding to something concealed from direct observation. Light could not expose it, but gravity continuously revealed its presence. By tracing how light curved around distant structures, astronomers effectively mapped invisible matter, outlining enormous formations that emitted no glow while still accounting for most of the gravitational influence in those regions. This mismatch demonstrated clearly that the unseen component was not some tiny adjustment added onto ordinary matter. It dominated the system. Visible material represented only a small fraction of the total mass affecting gravitational motion. The hidden companion was vastly more abundant, shaping galaxies and clusters in ways the visible portion never could. Even when astronomers pushed estimates of faint stars and dim gas clouds to their limits, the missing mass remained overwhelmingly large. Whatever this hidden partner was, it had to be fundamentally different. It could not simply be ordinary matter hiding in darkness. It neither emitted radiation nor absorbed or reflected it. Something so dark yet so massive had to behave differently from the familiar matter making up planets, stars, and people. Another important clue came from studies examining how galaxies formed in the early universe. Visible matter alone could not gather quickly enough to create galaxies within the time frames astronomers observed. Radiation in the young universe affected ordinary matter too strongly, preventing it from clumping efficiently during the earliest periods. Something unaffected by radiation needed to begin collapsing earlier, creating gravitational wells that ordinary matter could later fall into. This suggested that the hidden companion was already shaping the cosmos before the first visible stars ever ignited. Because it did not interact with radiation, it could collapse under gravity long before normal matter was capable of doing so. That early structural growth helped explain why galaxies formed with the shapes and distributions astronomers observe today. Visible matter appeared to assemble itself on top of an invisible framework, built by something dark and extremely abundant. If ordinary visible matter had been the only contributor, galaxies would look entirely different from the ones filling the universe now. They would likely be smaller, less stable, and arranged in very different patterns across space. Vast cosmic structures such as filaments and enormous voids would not display the large-scale arrangement revealed by astronomical surveys. When scientists modeled the universe using only visible matter, the outcome failed to resemble the large-scale cosmic web observed through telescopes. But once they added the unseen companion into those simulations, the structures began matching what astronomers actually measured across the universe. That hidden mass produced stronger gravitational wells, giving matter the ability to collect together and organize itself into the patterns we now observe. The close agreement between computer simulations and real observations reinforced the idea that this invisible component had been essential since the earliest stages of galaxy formation. Because this concealed companion does not interact with light, researchers depend entirely on gravity to uncover its existence. This approach is not unfamiliar in astronomy. It follows the same reasoning once used to discover previously unknown worlds. Neptune, for instance, was predicted before anyone directly observed it. Its gravitational pull subtly disturbed the orbit of Uranus, allowing astronomers to infer that another planet had to exist. They calculated where Neptune should be located, and eventually confirmed it through observation. The hidden gravitational companion follows that same principle, though on a far larger and stranger scale. Its influence stretches across enormous cosmic structures. Unlike Neptune, which could finally be seen through telescopes, this partner remains invisible to every method based on light detection. Even so, the logic remains unchanged. Gravity exposes the existence of objects, whether they can be seen or not. In several galaxies, stars orbiting near the outer edges moved as if the galaxies contained nearly 10 times more mass than visible starlight suggested. This made it clear that ordinary matter could not explain the full picture. The stars, clouds of gas and cosmic dust, represented only a small portion of the total mass required. Something additional had to exist to explain why galaxies remained stable instead of flying apart. This mismatch was not limited to a few unusual systems. It appeared repeatedly in almost every galaxy, where astronomers measured rotational motion. The missing mass, therefore, seemed to be a universal feature of galaxies, rather than a rare anomaly. Since the hidden companion could not be directly detected, scientists began searching for answers within particle physics. Whatever carried this mass needed to possess gravitational influence while lacking electromagnetic interaction. That meant it would neither absorb nor emit photons. It would not behave like ordinary atoms or molecules. It would not participate in chemistry or build the complex structures associated with normal matter. Instead, its primary role would simply be to contribute gravity. This significantly reduced the number of viable explanations. The hidden companion could consist of particles with mass, but no electric charge. Or perhaps it was made from entire populations of such particles that never bond together the way ordinary matter does. Other possibilities were explored as well, including the idea that gravity itself might operate differently across enormous distances. If gravity changed behavior on galactic scales, then perhaps the missing mass was unnecessary. However, these modified gravity theories struggled to explain the complete range of observations. Some could reproduce galaxy rotation curves reasonably well, but they encountered problems when dealing with galaxy clusters or measurements of the cosmic microwave background. They also failed to accurately account for gravitational lensing in merging galaxy clusters, where the distribution of mass clearly separated from the visible gas. Because of these issues, attention shifted back toward the existence of invisible mass rather than revisions to gravitational laws. The hidden companion also behaves differently from ordinary matter in another important way. It does not gather into dense clumps, collapse into stars, or settle into rotating disks. Instead, it spreads outward into enormous halos surrounding galaxies, creating a smoother distribution of mass. This helps explain why rotational patterns remain similar across many different galaxy types. Although visible galactic structures vary widely, the halo determines the broader gravitational environment. Because of this, stars move along paths controlled by the halo's mass distribution, which stretches far beyond the bright visible edges of galaxies themselves. Even though the hidden companion remains invisible, its behavior through gravity follows reliable patterns. This consistency allows astronomers to chart its presence indirectly. By measuring the movements of stars, gas clouds, and entire galaxies, researchers can identify where unseen mass must exist. These gravitational maps reveal that the hidden component is present everywhere, supporting structures throughout the cosmos. It surrounds galaxies in halos, spreads through galaxy clusters, and helps maintain the enormous cosmic web itself. Although it cannot be observed through ordinary methods, its gravitational effects are impossible to ignore. The fact that this companion behaves consistently across many different systems strongly suggests that it represents a major ingredient of the universe rather than some minor addition. This understanding shapes the way cosmologists interpret countless observations. The rate at which the universe expands, the clustering behavior of galaxies, and the temperature variations found within the cosmic microwave background all depend heavily on the total amount of mass present. Without the hidden companion, the universe would not behave in ways that match actual measurements. When scientists include it in their calculations, the results align far more closely with what telescopes detect. Since gravity responds equally to every form of mass, this hidden partner influences matter regardless of what kind of matter it happens to be. Both visible matter and unseen matter contribute together to the gravitational field, influencing movement across every scale in the universe. This relationship connects tiny systems like dwarf galaxies to enormous galaxy clusters and the vast structures stretching across cosmic space. The unseen companion mass participates in all of these systems. Since this companion cannot be directly observed through ordinary interaction, determining exactly what it is continues to be one of the major questions in modern research. Different detection experiments attempt to capture signs of it through delicate effects or extremely rare interactions, but no fully confirmed observation has been achieved so far. Even with that uncertainty, the gravitational evidence remains incredibly strong. The universe consistently behaves as if it contains far more mass than what human beings can actually see. This invisible partner affects galaxies in stable and predictable ways, making it a fundamental element of the cosmic environment. The concept that gravity may possess an unseen companion also reveals the limits of depending only on visible information. The universe is not arranged according to what shines. It is arranged according to mass, regardless of whether that mass can be seen or not. This realization changed the way astronomers approached observation itself. Light exposes only part of reality. Gravity exposes the remainder. As astronomers gradually recognized that the visible universe could not explain the gravitational behavior they were measuring, they began searching for methods capable of tracing the hidden component. Because this unseen material neither emitted light nor absorbed it, traditional observational techniques could not show where it gathered. Instead, scientists were forced to depend on indirect approaches, constructing maps of galaxies and clusters, not simply from visible light, but from the gravitational influence exerted on anything moving through or passing near those regions. Over time, these maps slowly revealed patterns of mass distribution that did not correspond to the luminous structures visible in telescopes. Areas that appeared empty frequently contained surprisingly large amounts of mass, while some brightly illuminated regions held much less hidden material than researchers originally expected. This showed clearly that mass throughout the universe does not follow visible light in any simple or predictable manner. The luminous structures were not reliable guides to the true gravitational terrain underneath. One of the earliest and simplest ways to chart the invisible component was to study stellar motion. By carefully measuring how fast stars traveled at different locations inside a galaxy, astronomers could estimate how much mass had to exist within those orbital regions. If stars were moving too rapidly for the visible material alone to keep them bound, then additional unseen mass had to be included in the calculations, even though nothing visible existed there. As more observations accumulated from many positions and directions, a repeating pattern appeared. The bright stellar disk represented only a small portion of the total mass, while the invisible component formed a massive halo extending far beyond the regions where visible starlight disappeared. These first maps were imperfect and based on limited information, yet they repeatedly pointed toward the same conclusion. The unseen matter was not merely present. It dominated the structure itself, shaping the galaxy's behavior more strongly than the visible material ever could. As observational technology improved, these mapping techniques became increasingly sophisticated. Radio astronomy allowed scientists to track the movement of hydrogen gas, which extended much farther outward than the stars themselves, and offered additional evidence about the surrounding gravitational field. The hydrogen moved in patterns that revealed the same flattened rotation curves previously observed in stellar motion. This strongly supported the idea that the invisible halo was not restricted to the regions occupied by stars. It continued far beyond them, remaining the dominant contributor to the galaxy's total mass. By combining measurements from stars together with measurements from gas, astronomers began building wider and more detailed maps of mass distribution. These maps revealed halos surrounding galaxies like gigantic envelopes, their densities slowly thinning with distance, while still stretching far enough to affect regions completely lacking visible matter. Although these rotation-based methods proved extremely valuable, they still could not provide a complete picture. They depended on material located inside galaxies, and therefore could not fully reveal structures existing in apparently empty regions or explain the interactions occurring between separate galaxies. Scientists needed methods capable of tracing mass even in places where no stars or gas could be detected at all. This led them toward gravitational lensing, a technique based on the way mass bends passing light. Light traveling across the universe does not always move along perfectly straight paths when massive objects lie nearby. Instead, its trajectory curves slightly according to the amount of mass present. This phenomenon gave astronomers a way to measure mass distributions without requiring any light from the object itself. The bending of distant background light became an essential tool for mapping the hidden framework of the cosmos. Weak gravitational lensing, one of the more subtle versions of this effect, proved especially important. It does not create dramatic distortions that are immediately obvious, but instead produces tiny, measurable alterations in the shapes of distant galaxies. By studying these delicate shifts across enormous numbers of galaxies, astronomers were able to reconstruct the distribution of mass lying in the foreground. This approach made it possible to build enormous maps covering vast sections of the sky. These maps didn't resemble the familiar pictures of stars, galaxies, or glowing nebulae that people are used to seeing. Instead, they revealed concentrations, threads, and sprawling regions of mass that failed to match visible cosmic structures. What astronomers were observing were essentially the outlines of dark matter itself, uncovered not through emitted light, but through the way its gravity warped and redirected light traveling across space. In regions filled with galaxy clusters, strong gravitational lensing became even more dramatic and easier to detect. Whenever massive concentrations gathered together in especially dense areas, they bent the images of distant galaxies into curved arcs and elongated streaks. Scientists could measure these distortions with remarkable precision, allowing them to estimate how mass was distributed with far greater accuracy than before. Some clusters revealed astonishing differences between the locations of visible matter and the mass detected through lensing measurements. In several cases, most of the mass appeared concentrated in regions containing very few visible galaxies at all. The brightest parts of a cluster were not always located where the true gravitational center existed. That separation became one of the clearest signs that the hidden component behaved differently from normal matter. One of the most famous cases involved two massive galaxy clusters colliding with one another. As the clusters moved through each other, the visible gas within them crashed together and slowed dramatically, creating an intensely hot and luminous region observable through X-ray telescopes. Yet, the gravitational lensing maps told a very different story. They showed that most of the mass continued moving forward beyond the gas, traveling alongside the galaxies instead of remaining with the slowed gas clouds. This divide between visible matter and gravitational mass became some of the strongest evidence that the unseen component did not interact with ordinary matter in familiar ways. The mass that kept moving did not appear to collide, compress, or heat up like the gas did. It passed through the collision with minimal resistance, suggesting that these invisible halos were made from something entirely unlike stars or hot gas. Observations like these strengthened the conclusion that the hidden mass possessed properties fundamentally different from anything humans encounter in everyday experience. The effort to chart these invisible shadows extended far beyond galaxy clusters alone. Large observational surveys were designed to trace the distribution of mass across enormous portions of the universe. These projects combined gravitational lensing measurements with the observed positions of galaxies and information gathered from the cosmic microwave background. Together, the data revealed a gigantic web-like arrangement stretching across incomprehensible distances. Bright galaxies tended to gather along dense filaments, yet the filaments themselves contained far more mass than visible galaxies alone could explain. These immense structures connected clusters together, forming a vast network of matter that shaped the architecture of the cosmos on scales too large to perceive directly. The resulting maps demonstrated that the unseen component was not limited to the outer halos surrounding individual galaxies. Instead, it occupied the regions between them as well, forming the structural backbone of the cosmic web itself. Even areas that appeared almost completely empty in ordinary optical images were shown through lensing maps to contain substantial amounts of hidden mass. This discovery transformed astronomers' understanding of large-scale cosmic structure. Rather than isolated galaxy clusters floating separately in darkness, the universe appeared as a connected system of massive pathways, guiding the placement of galaxies and influencing how they moved through space. These pathways often failed to line up neatly with visible structures. They stretched into regions where ordinary observations based on light revealed nothing remarkable at all. Yet gravity made it unmistakably clear that these areas were far from empty. The maps demonstrated that the unseen mass played a central role in building structure throughout the entire universe. The surveys also uncovered differences in density, revealing regions where the hidden component gathered more heavily, and other areas where it spread more thinly. Those variations shaped how galaxies emerged, how clusters evolved, and how matter flowed over billions of years of cosmic history. Areas with greater density attracted larger amounts of visible matter, while lower density regions expanded into enormous cosmic voids. The arrangement of dark matter created the underlying framework upon which all large-scale cosmic structure developed. It affected everything from the distances between galaxies to the forms of galaxy clusters and the development of enormous filaments crossing space. These maps transformed dark matter from a purely theoretical concept into something measurable within the structure of the universe itself. Another important way of tracing mass came from studying how galaxies group together across different distances. The clustering pattern depends strongly on the way matter interacts through gravity. If the universe contained only ordinary visible matter, the clustering patterns astronomers observed would look drastically different from reality. By comparing telescope observations with advanced computer simulations, scientists estimated how much total mass had to exist in different regions of space. Again and again, the results showed far more mass than visible matter alone could explain. The observed clustering matched simulations that included a dominant invisible ray influencing cosmic structure. This provided further support for the idea that unseen mass controlled the large-scale arrangement of galaxies throughout the universe. As observational methods became more advanced, astronomers were able to create increasingly detailed maps of mass inside individual galaxies. By examining the motion of stars, the behavior of interstellar gas, and in some situations the effects of gravitational lensing, researchers reconstructed how mass was spread throughout these systems. What these reconstructions consistently revealed was that dark matter halos extended far beyond the regions that emitted visible light. In many galaxies, the halo reached several times farther outward than the bright stellar disk itself. The glowing stars represented only a compact central portion sitting inside a much larger reservoir of mass. Although the exact structures differed somewhat between galaxies, the broader trend remained remarkably consistent. The visible material was not the dominant source of the galaxy's gravitational pull. Instead, it accounted for only a relatively small fraction of a much larger framework shaped by invisible matter. Certain galaxies offered especially valuable opportunities for more precise mapping. Some systems were positioned almost edge-on when viewed from Earth, making it easier for astronomers to measure how stars moved vertically relative to the galactic plane. These observations allowed scientists to investigate how mass was distributed not only outward from the center, but also above and below the disk itself. The results showed that visible matter alone could not explain the vertical stellar motions being observed. Extra mass had to exist throughout the surrounding halo. These improved maps provided a much clearer understanding of how the unseen components enveloped galaxies and affected motion in ways the luminous material by itself could never fully explain. In other situations, dwarf galaxies supplied particularly powerful evidence. These smaller galaxies often possessed extremely little visible matter, yet the stars within them moved as though far more mass existed than astronomers could directly observe. Since dwarf galaxies are relatively simple systems with fewer complicated interactions, they became ideal environments for studying invisible mass. The maps derived from stellar motion revealed extraordinarily high ratios of unseen matter compared with visible material. In certain cases, the luminous portion was barely detectable at all, while the gravitational influence remained surprisingly strong. This demonstrated that the unseen component was not merely following visible matter in fixed proportions. It existed independently and could dominate even in regions where ordinary visible material was scarce. As these mapping techniques continued improving, astronomers also created increasingly sophisticated simulations designed to compare theoretical models with real observations. These simulations included both visible matter and invisible components, enabling researchers to examine how different mass distributions influence the formation of galaxies and galaxy clusters over time. When the simulations incorporated unseen mass, the resulting cosmic structures closely resembled the universe astronomers actually observed. When the invisible component was removed, however, the simulated universe failed to reproduce many essential features and looked dramatically different from reality. Because of this, maps of unseen mass became crucial tools for testing and validating cosmological models. They refined estimates of how much invisible material existed throughout different regions of space and clarified how strongly it shaped cosmic evolution. The effort to map invisible matter also reached back toward the earliest stages of the universe itself. By analyzing the cosmic microwave background, astronomers could estimate how matter was distributed shortly after the universe first emerged. These ancient maps were indirect, yet they revealed the original seeds from which later structures developed. Tiny variations in the background radiation represented density fluctuations that eventually expanded into galaxies and clusters. The quantity of matter required to generate those fluctuations exceeded visible matter by a very large margin. This strengthened the conclusion that dark matter had influenced the universe from extremely early times. The maps of the young universe aligned closely with later maps of galaxies and clusters, producing a coherent picture of invisible mass-shaping structure across billions of years of cosmic history. Across all of these methods, the conclusions remained strikingly consistent. The unseen matter formed immense halos surrounding galaxies, filled galaxy clusters, stretched across giant filaments, and helped shape the enormous cosmic web spanning the universe. These maps offered astronomers a way to visualize structures that ordinary light alone could never expose. They did not rely on how bright galaxies appeared or whether stars were present. Instead, they traced mass directly through gravity's influence on motion and light itself. In doing so, these maps transformed humanity's understanding of space, changing it from what once seemed like a mostly empty background into a dynamic landscape crowded with invisible structures guiding the visible universe. When astronomers widened their perspective beyond single galaxies and clusters, they discovered that matter throughout the cosmos was not distributed randomly. Instead, it followed immense patterns extending across astonishing distances. These arrangements were neither simple nor evenly spread. They resembled a gigantic network made of interconnected regions, where dense concentrations of matter were linked by elongated structures stretching across space. Such formations were not immediately obvious when observing light alone. They became visible only after enormous surveys mapped the positions of countless galaxies across huge portions of the sky. As the amount of observational data increased, the arrangement of galaxies gradually revealed a larger structure, hinting at deep underlying forces shaping the universe itself. The galaxies were not simply wandering through space independently. They traveled along routes shaped by something that had already influenced their arrangement long before the galaxies themselves became visible. The massive surveys created to map galaxy positions were not originally intended to reveal a giant web-like framework across the universe. Their purpose was to study clustering, calculate distances, and better understand cosmic expansion. But as more and more observations were gathered over time, astronomers began noticing a remarkable pattern. Galaxies were not distributed evenly in all directions. Instead, they appeared to collect along stretched, elongated regions. These structures linked enormous clusters together, forming bridges made of matter. Between those bridges existed immense, empty-looking regions where very few galaxies could be found, creating gigantic cosmic voids. This pattern did not resemble a random spread of isolated points. It suggested that some deeper distribution of mass was determining where galaxies were able to form and where they were not. The visible universe outlined a kind of enormous network, yet the glowing matter people could actually see represented only a small fraction of the total mass responsible for shaping these structures. To understand why this gigantic network emerged, astronomers turned to computer simulations that modeled how matter behaved under gravity across billions of years. When those simulations included only ordinary visible matter, the resulting universe appeared far too smooth and failed to produce the massive structures seen in real observations. But once an unseen component was added as the dominant source of mass, the simulated universe suddenly began creating a network that closely resembled what galaxy surveys revealed. This invisible mass altered the gravitational landscape across enormous distances, producing regions where matter naturally gathered and other regions where very little accumulated. Visible galaxies followed those patterns because they formed inside the deeper gravitational wells produced by the hidden material. These simulations demonstrated that the universe's large-scale structure began with tiny differences in density that existed shortly after the beginning. Over time, gravity slowly amplified those slight variations, pulling material toward the denser areas. The invisible component, because it did not interact with radiation the way visible matter did, could start collapsing earlier. It laid down the foundation that everything else would eventually build upon. As this unseen material clumped together, it formed long, extended strands of mass, connecting larger concentrations. Those strands eventually became the framework of the cosmic web itself. Only afterward did ordinary visible matter cool enough to settle into those structures, creating galaxies and clusters along the densest regions of the web. The word thread should not create the impression of something tiny or fragile. These structures are unimaginably vast, stretching across tens or even hundreds of millions of light years. They contain extraordinary amounts of mass, most of which remains invisible. Galaxies line these enormous strands almost like beads attached along a wire, collecting in areas where density becomes greatest. Between these gigantic filaments lie immense voids that contain very little accumulated matter. These regions are not completely empty, but they possess far less material than the surrounding structures. Their existence reflects the hidden distribution of the unseen component and how gravity creates deep wells in some places while leaving others comparatively barren. Creating maps of this cosmic web required several different observational methods working together. Galaxy surveys supplied the overall arrangement by charting where galaxies were located throughout space. Gravitational lensing added information about the hidden mass underneath, revealing where the invisible component was concentrated. Measurements of the cosmic microwave background exposed the ancient seeds that later developed into this enormous network. Together, all these observations built a consistent picture of a universe shaped primarily by invisible mass. Even though galaxies illuminated the web and made it visible to observers, the web itself had already been defined by the unseen component long before the first galaxies ever formed. The cosmic web is not frozen or motionless. It continues evolving as gravity steadily pulls matter inward over immense spans of time. Giant clusters grow larger where the web intersects. Filaments stretch, shift, and develop as material flows through them. Galaxies travel within these structures, guided constantly by gravitational attraction. The hidden component influences those motions, shaping how structures change across billions of years. Simulations indicate that matter moves along these filaments in a slow and continuous flow, driven toward the densest regions by gravity. The invisible mass acts as the main force directing this movement, while visible matter follows behind it. One of the strongest arguments supporting the cosmic web model is how accurately observations match theoretical predictions once the unseen component is included. This agreement was never guaranteed from the beginning. The web-like arrangement might have turned out to be coincidence or the result of some entirely different unknown process. Yet simulations reproduce the observed structures successfully only when invisible mass is added to the equations. Without dark matter, the structure of the universe would look profoundly different. Galaxies would not cluster in the same patterns. Filaments would fail to emerge. Voids would not stand out so dramatically. The entire large-scale architecture of the cosmos would lose much of the complexity and detail that astronomers actually observe today. Astronomers also examine the dynamic behavior of galaxies moving within the cosmic web itself. Galaxies located near filaments often drifted toward them, guided by gravitational gradients produced by invisible mass spread throughout space. This movement, recorded through extensive observational surveys, exposed the pathways along which matter flowed across enormous cosmic distances. The measured behavior closely matched theoretical models that incorporated dark matter into their calculations. These large-scale flows helped scientists understand how galaxy clusters increased in size and why galaxies accumulated in particular locations rather than others. The observable universe appeared to travel along routes established by the hidden framework of the cosmic web. Additional discoveries emerged when researchers analyzed how galaxies positioned themselves around these filaments. The galaxies frequently showed preferred alignments. In many cases, they pointed along the same direction as the filament itself. That orientation suggested the gravitational influences shaping galaxies were not produced only by visible matter, but by the much larger architecture of the cosmic web surrounding them. The unseen mass formed an environment that affected how galaxies spun, interacted with neighboring systems, and gradually evolved over time. Even delicate characteristics of galaxies, including the direction they faced, contained clues about the distribution of dark matter beneath the visible universe. The enormous voids separating the filaments also became an important source of information. These vast and nearly empty regions reacted sensitively to the arrangement of unseen mass elsewhere in space. The dimensions and geometry of the voids depended on how invisible matter clustered in surrounding regions. Observations revealed that the sizes of these voids aligned remarkably well with predictions from models containing dark matter. They were not simply accidental pockets of emptiness scattered randomly across the universe, but regions where gravitational forces from surrounding structures controlled the movement and distribution of matter. Understanding these voids became just as significant as examining the dense clusters, because both contributed essential pieces to the overall structure of the cosmos. The cosmic web demonstrated that dark matter was not confined to isolated halos surrounding individual galaxies. Instead, it stretched across incomprehensible distances, forming continuous structures that shaped the entire observable universe. Galactic halos connected through massive filaments, building a vast and interwoven network of mass. Visible matter existed inside this framework, but it did not create the framework itself. Rather, the web directed visible matter, determining where galaxies would emerge and influencing the paths of their evolution. When astronomers observed galaxies at extreme distances, they were effectively looking back into the earlier stages of cosmic web formation. Those young galaxies appeared in areas where the concentration of unseen mass was slightly greater than average. Although the universe at that time was younger and less structured, these early formations already hinted at the same large-scale pattern visible today. The cosmic web did not suddenly appear all at once. It developed slowly over immense periods of time under the influence of invisible gravitational forces. The early universe contained only tiny and faint irregularities that gradually expanded into the gigantic filaments and clusters observed in the present era. The relationship between the cosmic web and dark matter became even clearer through studies of temperature variations in the cosmic microwave background. These faint fluctuations preserved information about differences in density that existed shortly after the universe began. Over billions of years, gravity amplified those tiny differences, eventually creating the vast web-like arrangement seen across space today. The quantity of dark matter required to reproduce the observed microwave background fluctuations matched the amount needed to explain the large-scale distribution of galaxies and cosmic structures. This agreement across completely different periods in cosmic history strengthened the evidence that dark matter influenced the universe from its earliest moments onward. While visible matter responded to the gravitational pull generated by the web, it also contributed to smaller and more localized details. Gas cooled over time and settled into the densest regions, eventually giving birth to stars and galaxies. Those visible systems later collided, merged, and evolved into more complex structures. Yet the broader patterns controlling these events remained tied to the invisible mass beneath everything. Ordinary matter could reshape local environments, but it could not fundamentally alter the overall structure of the web itself. The underlying framework remained governed by dark matter. As technology and observational methods advanced, astronomers produced increasingly sophisticated reconstructions of the cosmic web. Massive galaxy surveys collected enough information to map filaments across three-dimensional space. These reconstructions revealed an intricate arrangement of clusters, voids, and connecting strands extending across enormous cosmic scales. The light emitted by galaxies traced portions of the web, yet it became increasingly obvious that most of the web's total mass remained unseen. Dark matter created the structure itself, while galaxies merely illuminated certain sections without exposing the entire framework. Attempts to chart dark matter directly also continued through gravitational lensing observations. In some locations, lensing measurements revealed filaments containing very little visible matter, despite possessing tremendous amounts of mass. These dark filaments were extraordinarily difficult to detect without lensing techniques, yet they served a crucial role in linking galaxy clusters together. Observations of these structures offered even more evidence that invisible mass spread throughout immense cosmic networks, rather than existing only in isolated halos surrounding galaxies. These linking regions were essential pieces of the cosmic web, directing the movement of matter throughout the universe. The web itself brought together many different parts of cosmology into one connected picture. It tied the behavior of galaxies to the arrangement of mass across enormous distances. It connected tiny fluctuations from the early universe to the immense structures that exist today. It revealed that the same invisible substance responsible for galaxy rotation and the stability of galaxy clusters was also responsible for shaping the universe on its largest scales. Dark matter was not operating only in isolated regions. Its influence extended across the entire cosmos. Studying the cosmic web also helped astronomers understand why galaxies developed such different shapes and sizes. Galaxies forming where multiple filaments intersected often became much larger because matter continuously flowed toward them from several directions at once. Smaller galaxies that formed along individual filaments usually grew more gradually. These differences depended heavily on how mass was distributed within the web itself. The invisible component controlled the gravitational pathways, while ordinary visible matter simply followed those routes. This connection between galaxies and the web clarified many of the observed differences in galaxy structure and scale. As observations improved over time, the cosmic web appeared increasingly intricate, with smaller filaments branching away from larger ones, linking galaxies to clusters and clusters to enormous superclusters. The complexity closely resembled computer simulations that included dark matter. When dark matter was removed from those simulations, the patterns changed dramatically. The web either collapsed too rapidly or failed to develop with sufficient strength. The remarkable agreement between observations and simulations containing dark matter became some of the strongest evidence supporting the role of this unseen substance in shaping the universe. The cosmic web still stands as one of the clearest examples of how invisible mass guides cosmic evolution. It demonstrates not only where matter gathers, but also how matter flows and transforms across time. The visible universe reveals only part of the story. Beneath it lies a hidden distribution of mass, dominated by dark matter, building the structure and directing the formation of everything we can observe. As astronomers continued studying the universe through galaxy rotation curves, gravitational lensing, and large-scale surveys, the evidence repeatedly pointed toward an invisible mass affecting everything around it. Recognizing that some unseen component existed was only the beginning. The harder task involved determining what that hidden substance could actually be, which also required understanding what it could not possibly be. Eliminating possibilities became just as important as making direct observations. Every proposed explanation had to be tested against the gravitational evidence, the distribution of galaxies, the behavior of clusters, the cosmic microwave background, and the way structures developed across billions of years. If an explanation failed to match these observations, it had to be rejected. This gradual process of narrowing possibilities shaped our understanding of dark matter, not by directly revealing its identity, but by excluding what it was not. The earliest and simplest explanation suggested that the missing mass might simply consist of ordinary matter that was extremely difficult to observe. Perhaps the universe contained huge numbers of dim stars too faint for telescopes to detect. Maybe enormous populations of small cold bodies, such as brown dwarfs, wandering planets, or dead stellar remnants, drifted silently through space without producing visible light. These ideas seemed reasonable because they did not require introducing anything entirely new or unfamiliar. Many astronomers initially favored these possibilities because they fit comfortably within already known forms of matter. If faint stars or cold objects explain the missing mass, there would be no need to alter existing physics. But as observations became more detailed, this explanation gradually stopped working. Surveys using many different wavelengths searched for faint stars and cold hidden objects. Infrared observations were especially useful for detecting dim and cool bodies. The results showed that while such objects certainly existed, there simply were not enough of them to explain the enormous amount of missing mass. The amount of matter contained in faint stars and cold objects turned out to be far below what galaxies required. Even after counting every possible hidden object, the total mass remained only a small fraction of what was necessary to keep galaxies gravitationally stable. This effectively ruled out the idea that dark matter could be explained only by dim stars or cold leftover debris. Another possibility suggested that vast clouds of dark gas accounted for the missing mass. Gas can sometimes be difficult to detect if it remains cold and emits little radiation, but gas still interacts with light in other measurable ways. It can absorb radiation from distant background sources or produce emissions when particles collide. Astronomers searched for evidence of huge quantities of cold gas using radio telescopes capable of detecting very specific signals. The expected signatures never appeared in the required amounts. In addition, if most of the missing mass consisted of gas, that gas would affect stellar motion and would heat up through collisions between particles. Those effects never appeared in observations. Huge amounts of gas could not simply stay hidden forever, so gas alone could not explain the majority of the unseen mass. Scientists also explored the possibility of compact objects like black holes. Perhaps enormous populations of tiny black holes, or somewhat larger ones scattered throughout galaxies, could provide extra mass while producing no visible light. But black holes affect nearby objects through gravity in measurable ways. If galaxies contained vast numbers of them, astronomers would notice stronger disturbances in the arrangement and movement of stars. Researchers also searched for microlensing events, temporary increases in brightness that occur when a compact object moves between Earth and a distant background star. Even objects that emit no light can reveal themselves through this effect. Although some compact objects were detected through microlensing studies, the number of events was far too low to explain the enormous amount of missing mass. This largely eliminated the idea that galaxies were crowded with countless small black holes or similar dense remnants. Ordinary matter, regardless of its form, always interacts with radiation in some manner, either by absorbing it, scattering it, or emitting it. If the unseen mass consisted of ordinary matter, some detectable signature would appear somewhere in the electromagnetic spectrum. Yet observations made across many different wavelengths consistently failed to uncover such evidence. This gradual elimination process strongly suggested that dark matter could not be composed of the same familiar particles that build stars, planets, gas clouds, or cosmic dust. The unseen mass required to hold galaxies and galaxy clusters together had to be something fundamentally different. It could not behave like ordinary matter or respond to light in the same familiar way. That conclusion pushed scientists toward entirely new possibilities beyond the standard catalogue of astronomical objects. Before turning toward unknown particles, some researchers questioned whether gravity itself might operate differently across enormous cosmic distances. If gravity changed under specific conditions or at very large scales, then perhaps the missing mass was not truly missing at all. Maybe the problem came from the equations being used to calculate mass in galaxies and clusters. This proposal attracted attention because it avoided introducing an entirely new form of matter. Instead, it modified the mathematical framework used to interpret astronomical observations. Theories of modified gravity attempted to reproduce galaxy rotation curves without requiring invisible mass. Certain models successfully explained some galactic behavior, particularly within individual galaxies themselves. However, difficulties appeared once these modified gravity theories were compared against a broader collection of observational evidence. Galaxy clusters still required additional unseen mass to explain their behavior. Gravitational lensing observations, especially in systems where hot gas had separated from galaxies, demanded the presence of a component that barely interacted with ordinary matter. The cosmic microwave background created even stronger constraints. The tiny temperature variations and their detailed structure depended heavily on how much mass existed in the early universe. Modified gravity by itself could not reproduce those observed patterns. Computer simulations using only altered gravitational laws also failed to recreate the universe's large-scale structure accurately. They managed to explain isolated observations, but not the entire collection of evidence together. Because of this, the idea that gravity alone could solve the missing mass mystery gradually lost support. Another suggestion involved neutrinos. These particles are incredibly abundant and possess extremely small masses. They interact only weakly with ordinary matter and can pass through planets, stars, and even human bodies almost without leaving a trace. In principle, if neutrinos carried slightly more mass than scientists originally expected, they could potentially contribute a meaningful fraction of the universe's missing mass. But neutrinos travel at extremely high speeds. Because of this rapid motion, they cannot gather efficiently into dense structures on smaller cosmic scales. Their speed prevents them from clumping together early enough to help form galaxies in the manner dark matter appears to require. Research into cosmic structure formation demonstrated that neutrinos alone could not produce the observed web-like arrangement of galaxies spread throughout the universe. They contributed a small portion of the total mass, but nowhere near enough to explain the overwhelming missing majority. Some scientists also wondered whether the discrepancy might come from mistakes in measuring galactic distances or misunderstandings about how galaxies produce light. Maybe galaxies contained far more stars than astronomers had estimated. Or perhaps thick dust clouds were concealing large amounts of light from view. However, as measurements improved, these uncertainties steadily decreased instead of growing larger. Infrared and ultraviolet observations expanded the detectable range of stars. Dust models became increasingly accurate. Galaxy surveys grew deeper and covered wider portions of the sky. Still, the missing mass problem remained unchanged. The gap between visible matter and gravitational effects did not disappear as observations became more precise. In fact, the evidence only became stronger. It became increasingly obvious that the phenomenon was genuine rather than a simple observational error or technical limitation. Some researchers eventually began considering whether entirely exotic astrophysical objects might exist in enormous numbers throughout the cosmos. These hypothetical objects would not behave like ordinary stars, planets, or any familiar celestial bodies known at the time. However, theories predicting those kinds of objects demanded entirely new physics, while offering no additional explanatory advantage beyond the dark matter models that already existed. Since there was no observational evidence supporting them, these ideas failed to resolve the missing mass problem and were eventually set aside. As more potential explanations were rejected, scientific attention gradually focused on forms of matter that did not interact with electromagnetic radiation in any detectable way. This unseen matter could not simply be hot gas, dim stars, cosmic dust, or compact astronomical objects. It also could not behave like ordinary matter during the universe's earliest stages. Whatever it was, it needed to avoid interacting with radiation while still exerting gravitational influence. From this, researchers arrived at the conclusion that dark matter had to be non-baryonic, Put simply, it was not made from the same particles that form ordinary atoms. It did not consist of protons, neutrons, and electrons arranged in familiar structures. Instead, it needed to be composed of particles possessing mass, while lacking electromagnetic interactions altogether. Excluding normal matter played a major role in shaping this direction of thought. Calculations connected to nucleosynthesis imposed strict limitations on the amount of ordinary matter that could exist throughout the cosmos. Measurements of the cosmic microwave background strengthened these restrictions even further. If dark matter had been composed of ordinary matter, then the temperature variations and chemical abundances observed in the early universe would not align with what scientists actually detected. These constraints became strong enough to dismiss the possibility that dark matter was simply a hidden version of familiar particles. As this process of elimination continued, scientific focus shifted toward unfamiliar categories of particles. These hypothetical particles would operate differently from anything ever directly observed. They would neither absorb nor emit light. They would not combine into atoms or molecules. They would take no part in chemistry of any kind. The only necessary interaction was gravity. Because of this, such particles could exist in enormous quantities without noticeably affecting radiation. Numerous particle candidates were suggested, but before investigating those possibilities more deeply, scientists still needed to eliminate other astrophysical explanations. One remaining question asked whether dark matter might actually be explained through large-scale cosmic structures that had not yet been fully understood. Perhaps galaxies and galaxy clusters behave differently because of environmental influences or massive cosmic motions. Yet these explanations collapsed when tested against systems where dark matter appeared distinctly separated from visible matter. The behavior of merging galaxy clusters, in which the unseen mass remained associated with galaxies instead of hot gas, directly contradicted the idea that the phenomenon resulted from environmental misunderstanding. Those observations demanded an additional component that did not collide or slow down the way gas and stars do. No alternative model could reproduce those results without including dark matter itself. Another proposal explored whether primordial black holes could account for the missing mass. Unlike black holes created from dying stars, primordial black holes might have formed shortly after the universe began, existing long before the first stars ever emerged. If enough of them existed, they could potentially explain the hidden mass. The concept held theoretical interest, but it required observational confirmation. Surveys searching for microlensing events produced significant constraints. Additional studies involving the cosmic microwave background also placed limits on how many primordial black holes could exist without disturbing the radiation patterns scientists observed. Although certain mass ranges remained theoretically possible, primordial black holes could not explain all dark matter. They may exist in limited numbers, but they could not account for most of the invisible mass in the universe. Through this slow and careful elimination process, the number of viable explanations steadily decreased. Ordinary matter in every known form was ruled out. Modified gravity theories failed to explain all observations consistently. Fast-moving particles, such as neutrinos, did not match the evidence from structure formation. Large populations of compact objects were excluded through gravitational lensing surveys. Primordial black holes survived only as a partial possibility. What remained was an unfamiliar form of matter, unlike anything directly known in everyday experience. This invisible component needed to consist of particles that did not interact with light, moved slowly enough to clump together early in cosmic history, and generated gravitational effects matching a vast range of astronomical observations. Eliminating impossible explanations did not reveal the true identity of dark matter, but it established firm boundaries around the mystery. It clarified that the unseen mass must satisfy a precise collection of properties. It needed to be abundant, gravitationally significant, electrically neutral, and capable of helping create the large-scale structures shaping the universe today. These limitations directed scientists toward investigating entirely new particle types and theoretical models that might eventually explain the missing mass problem. Once astronomers and physicists had eliminated every familiar form of matter, the search inevitably had to move toward possibilities existing beyond the limits of ordinary experience. The invisible mass responsible for shaping galaxies, galaxy clusters, and the enormous cosmic web had to consist of something able to influence gravity while remaining completely indifferent to light, heat, electric charge, and the usual forces scientists rely on to observe matter directly. Since telescopes were unable to expose it, researchers shifted their attention toward particle physics, where the possibility arose that this hidden mass could come from an undiscovered type of particle. These particles would need to obey the limitations established through decades of astronomical and cosmological observations. They could not move rapidly like neutrinos. They could not interact strongly with electromagnetic radiation. And they needed to begin forming structures very early in the universe's history. This narrowed the search toward particles massive enough to affect gravity, while still subtle enough to slip unnoticed through ordinary matter. When scientists first explored which particles might explain dark matter, they turned toward existing physical theories for direction. Particles are not simply imagined out of convenience. They emerge naturally as possibilities inside broader theoretical systems designed to explain nature as completely as possible. One of the earliest and most influential proposals suggested that dark matter could consist of weakly interacting massive particles, better known as WIMPs. These hypothetical particles would interact only through gravity and the weak nuclear force. The weak nuclear force governs certain forms of particle decay but plays no role in everyday human experience, which made it an attractive explanation for matter that remains effectively invisible. WIMPs were expected to possess masses far larger than neutrinos, allowing them to gather together early in cosmic history without moving too quickly through space. They would also remain stable across cosmic timescales, resisting decay into lighter particles. That stability was crucial because dark matter had to survive throughout the lifetime of the universe in order to continue shaping galaxies and larger structures. Part of the fascination surrounding WIMPs came from what became known as the WIMP miracle. Early calculations indicated that a particle with the approximate mass and interaction strength predicted for WIMPs would naturally leave behind exactly the right amount of dark matter after the universe cooled from its extremely hot beginnings. As the cosmos expanded, particles constantly formed, collided, and annihilated one another. If WIMPs were present, they would initially have existed in enormous numbers. Then, as temperatures dropped, their annihilation rate would slow until the remaining population eventually stabilized. Remarkably, the predicted leftover quantity closely matched the amount of dark matter astronomers inferred from observations across the universe. This apparent coincidence made WIMPs seem especially convincing. It connected cosmology and particle physics in a way that felt almost too elegant to dismiss. Because of this, scientists began creating experiments specifically designed to detect WIMPs directly. The goal was to capture rare interactions between WIMPs and ordinary matter. Even though these particles would almost never interact, researchers reasoned that a sufficiently large detector placed within an extremely quiet environment could eventually observe one of these uncommon events. This led to the construction of underground laboratories protected from cosmic rays and other background interference. Different experiments used methods ranging from liquid xenon detectors to cryogenic crystal systems capable of measuring incredibly tiny releases of energy produced when a WIMP collided with an atomic nucleus. The hope was that even the faintest recoil signal could provide direct proof that dark matter particles truly existed. As technology advanced, these experiments became dramatically more sensitive, eventually reaching levels where WIMPs should have appeared if the original predictions were accurate. Yet the anticipated signals never arrived. Every new generation of detectors pushed the limits even further, ruling out broader ranges of possible WIMP masses and interaction strengths. The continued absence of evidence slowly began raising difficult questions. It did not completely eliminate the possibility of WIMPs, because the range of theoretical properties remained wide, but it made the simplest versions increasingly difficult to support. The growing silence inside these detectors suggested that if WIMPs were real, they might be much more elusive than researchers first imagined or interact even more weakly than early models predicted. Although WIMPs received enormous attention for many years, they were never the only candidate. Another possibility emerged from attempts to solve an entirely separate issue in particle physics. This second candidate became known as the axion. Actions were originally proposed to resolve a symmetry problem connected to the strong nuclear force, but physicists soon realized these particles also possessed characteristics that made them excellent dark matter candidates. Unlike WIMPs, axions were expected to be incredibly light. They would interact so weakly with matter and radiation that they could move directly through enormous objects without producing any detectable traces at all. Even though axions would possess incredibly tiny mass, they could still exist in vast quantities, together adding up to a substantial amount of mass across the universe. These particles would not behave like normal matter in the usual sense of movement or clustering. Instead, axions would likely exist more like a field spread throughout space itself, where tiny fluctuations in density could create the gravitational effects associated with dark matter. Detecting axions demanded methods very different from those designed for WIMPs. One major strategy was based on the possibility that axions might transform into photons under the right circumstances. To test this idea, researchers built experiments using extremely powerful magnetic fields, along with highly sensitive instruments capable of searching for incredibly faint signals generated through axion-photon conversion. Because scientists did not know the actual mass of the axion, these experiments had to scan through a huge range of frequencies. The process advanced slowly, but progress continued steadily as researchers gradually widened the regions they could investigate. Much like WIMPs, axions still had not been directly observed, yet they remained one of the strongest candidates because they matched many of the physical conditions required for dark matter. Beyond WIMPs and axions, scientists explored additional possibilities involving particles predicted by theories attempting to unify the known forces of nature. One of the most discussed frameworks was supersymmetry, a theory proposing that every known particle possesses a heavier partner particle connected to it. Many of these hypothetical partner particles could potentially serve as dark matter candidates because they would be stable and massive enough to persist throughout cosmic history. Supersymmetry itself was originally created to address deeper theoretical problems within particle physics rather than to explain dark matter specifically, but its predictions fit surprisingly well with the need for unknown stable particles in the universe. If supersymmetric particles truly existed, at least one of them could possibly survive long enough to make up dark matter. Large particle accelerators searched for evidence of these particles by reproducing energetic collisions similar to conditions present shortly after the birth of the universe. Scientists hoped these collisions would create supersymmetric particles whose existence could be inferred through missing energy signatures appearing in detectors. Yet despite many experimental runs, no unmistakable evidence for supersymmetry emerged, leaving its dark matter possibilities unresolved and unconfirmed. Another important proposal involved sterile neutrinos. Unlike ordinary neutrinos, which interact through the weak nuclear force, sterile neutrinos would interact through gravity alone. That property would make them extraordinarily difficult to observe directly, which also made them attractive dark matter candidates. Sterile neutrinos would likely possess masses different from standard neutrinos as well. If they were sufficiently heavy, they could contribute a meaningful portion of the universe's missing mass. Their behavior during the early stages of cosmic evolution would also differ from ordinary neutrinos, potentially allowing them to cluster in patterns compatible with dark matter observations. Searches for sterile neutrinos mainly relied on indirect evidence, including attempts to identify particular features in X-ray emissions that could suggest sterile neutrino decay. A few observations appeared suggestive, but none provided firm confirmation. Physicists also explored even stranger possibilities. One concept suggested that dark matter might consist of fuzzy particles, an ultralight variety of particle whose wave-like behavior could affect the way cosmic structures formed. These particles would be so incredibly light that their wavelengths might extend across entire galaxies. Such behavior could influence how matter gathers on smaller scales, and might help explain certain mismatches between computer simulations and the galaxies astronomers actually observe. If fuzzy particles existed, they could prevent extremely tiny structures from forming while still permitting larger cosmic structures to develop normally. The proposal remained highly speculative, but it offered an interesting possible explanation for some detailed galactic properties. Other theories proposed massive particles capable of interacting through their own separate force beyond the forces already known in physics. These self-interacting particles might help explain unusual density patterns observed inside galaxies. In some galactic centers, astronomers found evidence suggesting dark matter appeared distributed more smoothly than basic models predicted. Self-interacting dark matter could potentially soften those dense central regions without disrupting large-scale cosmic structures, offering one possible explanation for the discrepancy. Research into this idea was still ongoing, with scientists continuing to investigate whether such interactions could remain consistent with all existing observations. Some hypotheses moved even farther beyond conventional ideas in physics. Theories involving hidden sectors proposed that dark matter could consist of entire groups of particles interacting with one another through forces completely disconnected from the familiar forces governing visible matter. These hidden sectors might possess rich internal dynamics while remaining almost entirely invisible to ordinary matter. Although these ideas remained speculative, they demonstrated just how wide the landscape of possibilities had become. As more evidence ruled out simpler explanations, researchers responded by developing increasingly imaginative particle models in an effort to understand the unseen matter shaping the universe. Despite the enormous range of proposed candidates, the investigation into dark matter always remained tied to the limits established through cosmological evidence. Any particle suggested as a possible explanation had to meet several important conditions. It needed to explain the total amount of mass revealed through gravitational measurements. It had to gather together very early in cosmic history, so it could create the initial foundations from which galaxies later formed. It needed to interact weakly enough to avoid appearing in earlier experiments, while still exerting enough gravitational influence to shape large cosmic structures. It also had to remain stable across billions of years, without disappearing. The candidate particles had to agree with the temperature variations observed in the cosmic microwave background as well. In addition, they needed to fit the large-scale arrangement of matter throughout the cosmic web. These requirements eliminated many possibilities, while continuing to direct the search forward. Researchers kept improving experimental methods. Some projects concentrated on identifying extremely faint signals that might appear when hypothetical particles interacted with magnetic fields. Other teams searched for traces of particle decay occurring somewhere in space. Certain experiments attempted to detect dark matter particles created when cosmic rays collided with the atmosphere or with underground instruments. Every approach focused on a different possible characteristic of these unseen particles. The fact that no direct detection had occurred so far did not prove the particles were absent. It only suggested that their properties could exist beyond the sensitivity of current instruments. One major difficulty in this search came from the possibility that dark matter interacts so weakly that observing it directly may be extraordinarily challenging. Detectors might need to become vastly more sensitive than they are now, or scientists might need completely different technologies altogether. Some researchers proposed constructing much larger underground laboratories, while others suggested placing detectors in space where interference from background noise would be reduced. Additional ideas involved developing entirely new materials that could respond differently when exposed to hypothetical particles. All of these efforts demonstrated how demanding the task truly was. Detecting something that almost never interacts with ordinary matter required incredible accuracy, persistence, and patience. Even without direct evidence, theoretical research continued generating fresh possibilities. Models examining different masses, interaction strengths, and particle behaviors opened an enormous landscape of potential explanations. Some theories focused on particles far too massive to be created inside existing accelerators. Others investigated particles so light that entirely new detection strategies would be required. Each proposal attempted to satisfy observational constraints without creating inconsistencies elsewhere in physics. The wide variety of theories reflected both the difficulty of the mystery and the determination to solve it. As the investigation advanced, scientists developed a stronger understanding of the deep connection between dark matter and particle physics. This invisible mass was no longer viewed as merely an astronomical curiosity. It became a possible doorway toward discovering forms of physics beyond current knowledge. The idea that entirely unknown particles might exist suggested the universe still contained hidden layers of reality waiting to be revealed. Although dark matter itself remained invisible, the scientific framework guiding its study continued becoming more refined and more convincing. The ongoing search for the unseen particles shaping the universe gradually directed researchers toward a collection of candidates that dominated scientific discussions for many years. These candidates were not selected randomly. They emerged from attempts to resolve unresolved problems in particle physics, while simultaneously matching the demands imposed by astronomical observations. The invisible mass had to behave in a way that allowed it to shape galaxies and galaxy clusters, create early cosmic structures, and survive for billions of years without interacting noticeably with light or ordinary matter. Every proposed particle needed to explain these properties. Over time, several possibilities became central to the search, including weakly interacting massive particles, axions, and other hypothetical particles capable of passing through matter almost completely unnoticed. These mysterious candidates possessed different characteristics, yet they all shared one critical feature: they could contribute mass without exposing themselves through electromagnetic interactions. Weakly interacting massive particles eventually became one of the primary focuses because they appeared naturally within multiple theoretical models. If such particles existed, they would interact through gravity and the weak nuclear force while remaining invisible to light. This behavior matched the requirement for dark matter to stay hidden while still affecting the motion of stars and galaxies. Early calculations suggested that WIMPs could have formed abundantly during the earliest moments of the universe. As cosmic temperatures dropped, these particles would have collided and annihilated according to the strength of their interactions. The quantity remaining afterward aligned remarkably well with the amount of invisible mass inferred from astronomical observations. This remarkable coincidence pushed physicists to consider WIMPs as serious candidates because they seemed to provide a clean bridge between particle physics and cosmology. Since WIMPs were predicted to interact only very weakly with ordinary matter, scientists designed experiments capable of detecting the incredibly small bursts of energy produced if a WIMP struck an atomic nucleus. Such interactions were expected to happen extremely rarely, meaning the detectors needed extraordinary levels of sensitivity. To minimize contamination from cosmic rays and natural radiation, these instruments were installed far beneath the Earth's surface, inside deep mines or specially constructed underground laboratories carved into mountains. Some experiments relied on enormous tanks filled with liquid xenon, while others used cryogenic crystals sensitive enough to register tiny vibrations almost impossible to measure. The expectation was that, eventually, one of these detectors would capture an unmistakable signal produced by a passing WIMP. Although a few early results briefly appeared promising, later analysis and additional testing eventually ruled them out. Rather than stopping the search, these disappointments motivated scientists to construct even larger detectors, lower background interference further, and improve experimental precision. In spite of all these efforts, no verified WIMP detection has ever been confirmed. This lack of evidence did not completely remove the possibility of WIMPs, because their exact characteristics were never firmly established. They might interact with matter far less often than researchers originally assumed, or possess masses outside the predicted range. Nevertheless, the simplest WIMP models gradually became less convincing as experiments excluded larger and larger regions of possible interaction strengths and masses. Physicists kept developing and testing revised theories, but the excitement that once surrounded WIMPs slowly evolved into a more careful and restrained attitude. The continuing inability to detect them suggested that, if WIMPs were real, they might exist beyond the capabilities of present-day instruments. While WIMPs dominated much of the discussion, another possible particle appeared from an entirely different branch of physics. Actions were first proposed to solve a symmetry problem connected to the strong nuclear force. They were not originally invented to explain dark matter, yet their properties matched many of the requirements dark matter seemed to demand. Actions would be extraordinarily light, and would interact with matter and radiation so weakly that they could move through planets, stars, and even detectors almost without leaving any observable trace. Even so, their total abundance throughout the cosmos could still provide the missing mass affecting the structure of the universe. Unlike WIMPs, actions would not have formed through the same processes in the early universe. Instead, they would behave more like a field, permeating all of space itself. Their existence would influence gravity without necessarily behaving like conventional particles in the ordinary sense. Detecting axions required experimental methods completely different from those designed for WIMPs. One major strategy relied on the theoretical prediction that axions might transform into photons when traveling through extremely strong magnetic fields. Scientists built experiments capable of creating carefully controlled magnetic environments where this conversion could potentially happen, using ultra-sensitive instruments to search for faint photons that otherwise should not exist. These experiments scanned across many different frequencies, because the mass of the axion, which determines the resulting photon frequency, remained unknown. Progress moved slowly because each possible mass range had to be tested separately, one at a time. Although no confirmed axion discoveries had yet been made, researchers continued expanding the frequency ranges under investigation. The results did not eliminate actions as possibilities, but they steadily narrowed the regions where such particles might still exist. Another reason axions continued attracting attention was that they fit well with how structures formed throughout the universe. Their behavior allowed them to contribute gravitational mass in ways that supported the growth of galaxies and massive clusters. They could gather together on enormous scales while avoiding certain small-scale complications that challenged other dark matter theories. Because their interactions were so weak, they also would not disturb the delicate early universe conditions preserved in the cosmic microwave background. These characteristics kept axions attractive as dark matter candidates, particularly while WIMP experiments repeatedly failed to produce evidence. Additional mysterious candidates also emerged from theories extending beyond the standard model of particle physics. Supersymmetry introduced a large family of hypothetical particles. According to this framework, every known particle would possess a corresponding partner particle with different spin behavior. Some of these partner particles could be stable, heavy, and only weakly interacting, making them realistic dark matter possibilities. Supersymmetry also provided elegant answers to several deeper theoretical questions, including how particle masses remain stable and how the fundamental forces of nature might eventually unify. If supersymmetric particles truly existed, one of them could potentially explain dark matter. Particle accelerators attempted to produce these particles by recreating the extremely energetic conditions believed to have existed shortly after the birth of the universe. Researchers searched for unusual collision events in which energy appeared to disappear unexpectedly, implying that invisible particles had been created, which passed through the detectors without interacting. Although particle accelerators detected many effects that matched predictions from the standard model, they failed to uncover any unmistakable evidence of supersymmetric particles. This did not completely rule out supersymmetry, since the theory permitted partner particles to exist across a broad spectrum of masses. Those particles might simply be too massive for present-day accelerators to reach, yet the continuing absence of evidence introduced growing doubt. Supersymmetry had long stood as one of the leading theoretical frameworks in physics, but without the expected signals, its role as an explanation for dark matter became increasingly uncertain. Researchers revised and refined the models, though the lack of confirmation pushed many scientists to investigate different possibilities. Another category of proposed particles involved sterile neutrinos, Ordinary neutrinos interact through the weak nuclear force along with gravity. Because they interact so rarely with normal matter, they are already extremely difficult to detect. Sterile neutrinos, however, would be even more elusive because they would not interact through the weak force whatsoever. Gravity alone would influence them, making direct observation vastly more difficult. Their possible existence emerged partly from attempts to explain unusual results seen in neutrino experiments. If sterile neutrinos possessed the correct masses, they could potentially account for dark matter. They would gather together early enough in cosmic history to shape the formation of large structures throughout the universe. Their decay processes might also generate detectable X-ray emissions. Certain observations revealed unusual lines within X-ray spectra that could hint at sterile neutrino decay, but none of these signals have been conclusively verified. Physicists also investigated theories involving particles with extraordinarily tiny masses. In some of these models, dark matter would behave less like separate particles and more like a massive wave extending across space. Such particles could possess wavelengths stretching through enormous portions of galaxies. Their wave-like nature would smooth smaller structures and create density distributions unlike those predicted by traditional WIMP theories. These distinctions could potentially explain some galactic observations more accurately. Detecting such particles demanded experimental methods capable of measuring extremely weak energy signatures, forcing researchers to develop entirely new detection techniques. Certain theoretical approaches expanded the idea of dark matter into the possibility of entire hidden sectors. These hidden sectors could function almost like a parallel form of particle physics, complete with their own interactions and internal structures. Particles existing inside those sectors might interact with one another through forces completely disconnected from ordinary matter. Such theories allowed for dark matter candidates displaying many different behaviors, including self-interacting particles that could potentially explain variations in galactic density. Even though these ideas remained highly speculative, they demonstrated how researchers were widening the search beyond more traditional concepts. As observational limits became more precise, scientists increasingly explored theories that moved further away from standard assumptions. Another proposal focused on massive composite particles created through interactions absent from the visible universe. These objects could behave very differently from elementary particles while remaining stable and abundant throughout cosmic history. Simulations investigated whether such particles could naturally emerge, and whether their existence would remain consistent with astrophysical observations. Although these concepts stayed largely theoretical, they illustrated how broad and diverse the search for dark matter had become. Across all of these theories, the proposed particles needed to satisfy the strict conditions imposed by the behavior of the universe itself. Those conditions acted as demanding tests. Any viable candidate had to explain not only the rotation curves of galaxies, but also the behavior of galaxy clusters, the temperature patterns visible in the cosmic microwave background, the development of the cosmic web, and the absence of electromagnetic interactions. The particles also needed to remain stable over cosmic timescales and travel at the proper speeds to clump together during the universe's early stages. Numerous candidates failed to meet one or more of these requirements, helping researchers narrow the field toward the most promising possibilities. Experimental investigations advanced alongside theoretical work. Some experiments relied on cryogenic detection systems designed to observe tiny vibrations caused by particle collisions. Others searched for photons generated within magnetic fields, hoping to identify evidence of axion conversion. Large underground detectors watched for extremely rare events using liquids maintained at carefully controlled temperatures. Particle accelerators continued looking for missing energy signatures that might reveal invisible particles escaping detection. Space observatories searched for X-ray or gamma-ray emissions that could originate from particle decay. Every method targeted a different possible property of these hypothetical particles. Although none of the experiments had yet delivered definitive proof, each new result helped refine existing theories and reduce the range of parameters where dark matter particles could still exist. The hunt for WIMPs also continued through the development of next-generation detectors, Even while the simplest WIMP models gradually lost favor, these detectors became increasingly massive and dramatically more sensitive, capable of probing interaction strengths far weaker than earlier experiments could measure. Researchers developed new methods to separate possible dark matter signals from the constant background interference surrounding every detector. Certain experiments introduced different target materials based on the idea that changing atomic characteristics could uncover patterns pointing toward WIMP interactions. Theoretical predictions also broadened, covering larger spans of masses and interaction behaviors, allowing the possibility of WIMPs to remain scientifically plausible. At the same time, axion research continued progressing steadily. Better magnet configurations, higher detector sensitivity, and faster scanning capabilities enabled scientists to investigate much wider frequency regions than before. Additional ideas proposed looking for axion-like particles through completely different strategies, including astrophysical observations or subtle influences on electromagnetic fields. Actions continued to remain strong candidates because they could explain dark matter without contradicting existing observations, even though detecting them required exceptionally difficult experimental techniques. Sterile neutrinos were also studied through indirect evidence. Astronomers searched through X-ray emissions coming from galaxies and galactic clusters, examining whether unusual spectral signatures might reveal signs of particle decay. From time to time, intriguing clues appeared, but none survived confirmation. Scientists expected that more advanced telescopes and increasingly refined analysis methods would eventually provide clearer conclusions. The wide variety of these elusive particle candidates demonstrated just how complicated the dark matter mystery truly was. Dark matter needed to be subtle enough to remain hidden from direct detection for decades, while still shaping the structure of the universe across enormous cosmic distances. It had to remain stable over immense periods of time, exist in large quantities, and exert strong gravitational influence. Every proposed particle attempted to meet these requirements in its own way, and each possibility demanded both theoretical investigation and experimental verification before it could be seriously accepted. As the number of hypothetical dark matter particles continued expanding, the problem of actually detecting them became even more important. If these particles interacted so weakly with ordinary matter that they could pass through planets, stars, and scientific instruments without leaving noticeable traces, then discovering them required extraordinary precision. Scientists began constructing experiments not to capture dramatic or obvious events, but to notice unbelievably faint disturbances. These disturbances were so delicate, they resembled footsteps too soft to leave marks in dust, yet they could still carry meaning if measured carefully enough. The experiments needed to observe the universe with a level of sensitivity that stretched technological limits, eliminating every possible source of interference until only the faintest whispers remained. The challenge was not simply about building enormous machines, but about isolation, patience, and recognizing how easily an unrelated signal could imitate the exact effect researchers hoped to find. Underground laboratories became essential to this effort. Since dark matter particles were expected to interact extremely rarely, detectors needed protection from particles that interacted constantly. Cosmic rays continuously strike Earth's surface, and if they reached the detectors freely, they would completely overwhelm the delicate instruments. By constructing laboratories beneath mountains or deep inside old mines, scientists used the Earth itself as a protective barrier. Thick layers of rock absorbed most incoming cosmic rays, lowering background interference enough for detectors to search for extremely weak interactions. Entering these underground facilities often involved traveling through long tunnels and carefully regulated chambers where every environmental condition was monitored closely. Even tiny fluctuations in temperature or humidity could affect detector performance, meaning stability was absolutely necessary. Inside these laboratories, many detectors used large amounts of specially selected materials capable of responding to extremely small energy deposits. Liquid xenon became one of the most commonly used substances because particles striking it could produce both flashes of light and electrical signals. When a particle collided with a xenon atom, the detector recorded a faint burst of light along with a tiny electronic response. By studying the timing and location of these signals inside the detector, researchers could evaluate whether the event resembled a possible dark matter interaction rather than ordinary background radiation. These experiments had to carefully separate normal noise, subtle chemical activity, radioactive contamination, and the rare interactions being searched for. Even minimal impurities inside the xenon could imitate a meaningful signal, which meant the purification process needed to be extraordinarily strict and precise. Other experiments depended on cryogenic crystals cooled to temperatures approaching absolute zero. Under such extreme conditions, the crystals became remarkably sensitive to tiny vibrations. If a dark matter particle transferred even a very small amount of energy into the crystal, the detector could potentially measure the effect. Scientists could distinguish between interaction types by analyzing how the deposited energy moved through the material. Vibrational signatures created by ordinary particles usually followed recognizable patterns, while hypothetical dark matter particles were predicted to generate different kinds of patterns altogether. Keeping temperatures at such extreme lows demanded highly advanced refrigeration systems that needed to function constantly without any interruption at all. Across all of these experiments, limiting unwanted noise became just as critical as identifying the actual signal researchers were searching for. Scientists needed to account for every possible source of background radiation inside the detector itself. That involved identifying radioactive isotopes contained within the materials used to construct the detectors, carefully measuring the activity levels of each component, and confirming that the surrounding layers of rock were not releasing stray signals into the system. Even the air inside the experimental chambers required continuous monitoring because radon gas could introduce unwanted particles capable of contaminating the detector readings. Minimizing these different forms of noise demanded extremely careful engineering decisions and the deliberate selection of construction materials. In spite of all this complexity, several experiments continued operating steadily for months and sometimes even years, slowly accumulating data over time. Every recorded event then had to be examined carefully to determine whether it resembled the predicted signature of dark matter. The majority of those events could eventually be explained through known physical sources. Only a small fraction remained uncertain, encouraging researchers to improve and refine their analysis methods further. From time to time, possible hints appeared that attracted serious scientific attention. These possible signals always required confirmation from multiple detectors in order to avoid reaching conclusions too early. Whenever a signal appeared in only one detector and failed to show up anywhere else, scientists treated it with considerable caution. In certain cases, these hints later vanished, once additional data was gathered or once previously unknown noise sources were discovered. While underground detectors focused on listening for collisions, other scientific projects searched for particle interactions through entirely different methods. Some experiments investigated whether dark matter particles might naturally emerge within cosmic environments. If specific particles were capable of decaying into photons or other measurable particles, telescopes on Earth and in orbit could potentially observe these decay signatures. Studies involving galaxies and galaxy clusters created opportunities to measure X-rays or gamma rays that might originate from dark matter decay processes. If researchers observed a particular energy line appearing repeatedly across multiple observations, it could suggest the existence of a particle with a specific mass. Several investigations produced possible candidate signals, yet none were ultimately verified as dark matter. Every time a promising energy line appeared, scientists needed additional observations to determine whether the source truly involved dark matter or whether it resulted from more ordinary phenomena, such as interactions occurring within extremely hot gases. Another major strategy involved searching for evidence of dark matter through particle accelerators. By smashing particles together at extraordinarily high energies, accelerators could potentially generate new particles that never appear naturally in ordinary environments. If dark matter particles were created during those collisions, they would not directly interact with the detectors. Instead, they would pass through unnoticed, leaving no visible tracks behind them. The detectors would only register missing energy and momentum. Physicists relied on this missing information to infer the possible existence of invisible particles. These experiments demanded highly controlled collision conditions, sophisticated detector systems capable of measuring outgoing particles precisely, and theoretical frameworks that could properly interpret the missing energy signatures. Although accelerators generated many unusual and interesting events, no unmistakable evidence of dark matter particles ever emerged. Some researchers instead focused on astroparticle techniques, searching for products created through interactions between dark matter particles and cosmic rays. If dark matter particles occasionally annihilated one another or decayed, those processes might produce ordinary particles that detectors could identify. Instruments placed in space measured the flux of electrons, positrons, and gamma rays. Any excess beyond expected background values could potentially suggest dark matter interactions. Interpreting these observations proved extremely difficult because many astrophysical phenomena were capable of producing nearly identical signals. Pulsars, supernova remnants, and other highly energetic cosmic objects generated emissions that complicated the analysis considerably. Even so, scientists continued using these observations to evaluate different dark matter models and examine whether certain interaction mechanisms remained physically plausible. As research efforts expanded further, some experiments adopted approaches that were increasingly creative and less traditional. Certain theoretical frameworks proposed that dark matter particles might interact with electromagnetic fields in extraordinarily subtle ways. Experiments designed to investigate these possibilities searched for tiny alterations in field behavior under tightly controlled laboratory conditions. Other theoretical ideas proposed measuring the direct gravitational influence of individual particles, although that possibility remained far beyond the limits of existing technology. Even so, these theoretical investigations encouraged scientists to continue developing entirely new detection methods, despite the fact that some of those concepts still remained highly speculative. One of the subtle difficulties in the hunt for dark matter was figuring out exactly where scientists should search for it. If dark matter truly filled the universe, then enormous amounts of it would also be flowing through Earth continuously. But because nobody knew how often it could interact with ordinary matter, experiments had to be designed around a very wide range of possible interaction strengths. The interaction rate might be so incredibly weak that collecting useful evidence could require many decades of observation. Because of this, even experiments that failed to detect anything still offered important scientific value. Every null result ruled out certain theoretical possibilities, reducing the number of viable models and helping direct future investigations more effectively. The search for dark matter never depended solely on single detectors or isolated laboratories working independently. Research teams from different countries and institutions shared findings, coordinated their efforts, and compared observations carefully. Experiments located around the world relied on different materials, environmental conditions, and detection techniques. This variety was essential because it prevented one specific source of background noise or one environmental issue from misleading the entire scientific community. If several independent experiments observed the same signal, the result would become far more convincing. If only one detector reported it, scientists would immediately investigate whether local environmental conditions or flaws in the equipment might have produced the apparent signal instead. The importance of redundancy also applied to the development of theoretical models. Physicists combined the outcomes from many different experiments to judge how plausible each proposed dark matter particle remained. If underground detectors ruled out certain interaction strengths, while particle accelerators excluded particular mass ranges, those eliminated regions pushed theorists toward different explanations. Computer simulations that incorporated dark matter interactions also helped researchers refine which particle properties were necessary to reproduce what astronomers actually observed in the universe. The constant exchange between theoretical predictions and experimental evidence formed an ongoing feedback process that steadily improved both sides of the research. Some experiments searching for axions relied on resonant cavities paired with extremely strong magnetic fields. The concept behind these experiments was that if axions traveled through the cavity, they could potentially transform into photons at very specific frequencies determined by their mass. To search for these possible signals, researchers needed to tune the cavity across different frequencies while monitoring for incredibly faint traces of energy. The major difficulty came from the enormous frequency range that had to be explored, since nobody knew the actual mass of the axion. Scientists were forced to adjust the equipment slowly and methodically, scanning one extremely narrow frequency interval after another. As these searches progressed, advances in detector sensitivity and cavity engineering increased the speed and effectiveness of the process. New experimental concepts also began exploring methods that no longer depended entirely on traditional cavity systems. Some approaches used plasma effects, while others relied on specialized materials that might react differently when exposed to axion-like particles. These alternative strategies expanded the search significantly, allowing researchers to investigate additional mass ranges that had previously been difficult to test. Yet the central challenge remained unchanged: finding a particle that interacted so weakly it could move through the entire planet without leaving any noticeable trace behind. Even so, every technological improvement allowed scientists to examine a larger fraction of the possible parameter space. The continuing effort to identify dark matter also motivated experiments focused on detecting its influence on astrophysical objects. Certain theoretical models suggested that dark matter might slowly accumulate inside stars or planets over long periods of time, potentially affecting how those objects behaved. Unusual interactions could alter energy transport within stars or modify their cooling rates. Researchers studied white dwarfs, neutron stars, and even Earth itself for subtle signatures that could provide indirect evidence for dark matter. Although none of these investigations had yet produced definitive confirmation, they opened additional pathways for exploring these hidden particles. No matter which technique scientists employed, the central obstacle always remained the same: detecting a signal so faint that it almost disappeared completely into the background. The technological demands pushed engineering and material science to extraordinary extremes. Detectors had to be constructed from materials containing exceptionally low levels of natural radioactivity. Sensors needed the ability to measure tiny energy deposits so small they would normally be dismissed as meaningless noise in almost any other scientific field. Environmental monitoring systems were required to maintain remarkably stable conditions for months or even years at a time. Every small detail mattered, because even the slightest imperfection could create a false signal capable of misleading researchers. The willingness to create instruments this sensitive reflected the understanding that dark matter would never reveal itself through ordinary observation. It was not something researchers could photograph directly, trap physically, or hold in their hands. Detecting it demanded patience and an intense focus on the tiniest disturbances inside systems engineered to remain as silent and undisturbed as possible. These experiments were not waiting for spectacular cosmic events. They were waiting for rare and minuscule interactions occurring with a frequency almost impossible to imagine. As experiments continued searching for extremely faint interactions, scientists also considered the possibility that the invisible particles shaping cosmic structure might sometimes collide with one another or create signals too delicate to appear under ordinary conditions. If dark matter particles possessed even the slightest ability to interact, those interactions might leave detectable traces in the correct environments. Astronomers examined distant galaxies, galaxy clusters, and the patterns hidden within cosmic radiation, looking for any indication that these unseen particles produced energy, radiation, or unusual structures that visible matter alone could not explain. The hope was that somewhere in those remote cosmic regions, dark matter might expose part of its nature through a rare collision or interaction capable of generating measurable byproducts. Every new observational technique offered another opportunity to test whether the hidden mass influencing the universe was doing more than simply exerting gravity. But the search proved difficult because the expected signals were incredibly weak, while the environments being studied already contained many ordinary processes able to create similar effects. Separating one possibility from another became a slow and careful effort involving theory, observation, and computer simulation. One important location researchers investigated was the center of galaxies, where dark matter densities were expected to be greatest. If dark matter particles occasionally collided and annihilated each other, that process could release energy as photons or other particles. Such emissions could appear as unusual radiation at specific wavelengths, standing apart from the normal astrophysical activity surrounding stars, gas clouds, and black holes. Certain telescopes focused on the center of the Milky Way, searching for gamma rays that might serve as evidence of dark matter annihilation. This area became a logical target because it contained enough matter to potentially increase the likelihood of interactions while remaining close enough for detailed observation. Early analyses suggested a possible gamma ray excess that could not easily be explained by ordinary sources. This attracted considerable attention because the signal resembled predictions made by several dark matter theories. However, as scientists examined the region more carefully, they discovered that pulsars and other astrophysical objects were also capable of producing similar excess radiation. The observations had to be analyzed with great caution to determine whether the excess truly reflected dark matter collisions or instead originated from populations of faint, unresolved objects that had not yet been catalogued. The crowded and complicated environment near the galactic center made isolating a single cause extremely challenging. Each time a promising signal appeared, researchers needed additional observations and more detailed analysis to eliminate competing explanations. As measurement techniques improved, many of the earlier hints became less persuasive. Some vanished entirely after updated models incorporated previously unidentified radiation sources. Others remained visible, but grew increasingly uncertain, preserving the possibility of dark matter interactions without providing definitive proof. Scientists also turned their attention toward dwarf galaxies orbiting the Milky Way. These systems were considered excellent targets because they contained very little gas and relatively few stars, reducing the number of ordinary astrophysical processes capable of imitating possible signals. If dark matter collisions produced gamma rays or X-rays, those emissions might stand out more clearly in such quiet environments. Multiple investigations searched these galaxies for unusual radiation, yet the results failed to reveal any consistent emissions above background levels. This lack of evidence did not eliminate the possibility of dark matter interactions, but it did place stronger limits on how powerful or frequent those interactions could be. If collisions occurred at all, they had to be weak or uncommon enough that their signatures remained invisible even in the cleanest observational environments. Beyond gamma rays, researchers searched for many other potential signals linked to dark matter interactions. Some theoretical models proposed that dark matter particles might slowly decay across billions of years, producing narrow spectral features detectable in X-ray observations. Telescopes designed to identify faint X-ray lines began examining galaxy clusters and galaxies for unexpected patterns. A few studies reported spectral lines that failed to match any known atomic transitions, leading to speculation that they could represent evidence of dark matter decay. Yet later observations frequently failed to reproduce those same results. In other situations, the reported lines appeared to depend strongly on instrumental sensitivity or calibration uncertainties, creating doubts about whether they represented real astrophysical phenomena or merely artifacts introduced during measurement. This cycle repeated throughout many different investigations. Potential signals appeared, generated excitement, and gradually weakened as larger amounts of data became available. Another branch of research focused on high-energy particles detected by instruments operating in space. If dark matter particles annihilated or collided in certain regions of the universe, they could generate electrons, positrons, or other energetic particles. Devices designed to study cosmic rays measured how these particles appeared across different energy levels. Occasionally, the collected data revealed small excesses that did not completely match the behavior expected from known astrophysical mechanisms. These unusual patterns led some researchers to wonder whether dark matter could be contributing to the signal. Yet, interpreting those results proved difficult, because pulsars and other highly energetic cosmic objects were also capable of generating very similar signatures. Separating possible dark matter effects from ordinary astrophysical sources demanded extremely careful modeling and analysis. As those models gradually became more refined and realistic, many of the observed excesses could eventually be explained without requiring dark matter at all. The anomalies remained scientifically interesting, but they stopped short of becoming convincing evidence. The effort to detect dark matter interactions also expanded toward galaxy clusters. These gigantic cosmic structures were believed to contain enormous quantities of dark matter, making them ideal environments where interactions could potentially become observable. Astronomers used telescopes to examine these clusters for strange forms of radiation or unusual signals that might emerge from dark matter collisions or decay. Certain investigations focused specifically on what happened when two galaxy clusters collided with one another. If dark matter particles were capable of interacting among themselves, they might slow down, scatter, or behave differently during these immense cosmic impacts. Observations of merging clusters created opportunities to compare the motion of visible matter with the inferred behavior of dark matter. Most of the evidence suggested that dark matter passed through such collisions with almost no detectable resistance at all, strengthening the idea that dark matter interacted extremely weakly, not only with normal matter, but also with itself. This behavior narrowed the number of viable theories, excluding models in which dark matter particles frequently collided. Even so, some theoretical models allowing weak self-interactions still remained consistent with the data. These scenarios proposed that dark matter particles might scatter only rarely, though still often enough to become measurable within extremely dense regions. Researchers continued testing these ideas by comparing maps of dark matter created through gravitational lensing with the observed arrangement of visible matter. Some computer simulations indicated that weak self-interactions could create subtle alterations in galactic density structures, but interpreting the observational evidence remained highly challenging. In many situations, the differences between simulated galaxies and real observations could also be explained through unrelated influences, such as gas dynamics or star formation processes. Because of this, efforts to use galactic structure as proof of dark matter self-interactions produced inconsistent outcomes and failed to deliver any definitive confirmation. One repeating pattern throughout these investigations was the appearance of signals that initially seemed exciting, but gradually lost strength after deeper examination. Researchers encountered this situation repeatedly across many independent studies. A gamma-ray excess might appear to match theoretical expectations at first, only to later be traced back to dim astrophysical sources that had previously gone unnoticed. A narrow X-ray feature could appear clearly in one instrument while remaining absent in another. A cosmic ray anomaly might continue attracting attention until newer observations finally revealed an ordinary astrophysical explanation. These quiet frustrations did not weaken scientific interest in dark matter, but instead demonstrated how difficult it was to detect something that interacted so infrequently with the universe around it. They also reinforced the importance of caution, careful interpretation, and independent verification from multiple experiments. Another major obstacle came from the limitations inherent in the instruments themselves. Telescopes did not maintain equal sensitivity across all energy ranges, and calibration procedures had to remain extraordinarily accurate to prevent instrumental noise from being mistaken for a genuine discovery. Analytical techniques continued evolving as scientists gained a better understanding of the instruments and their behavior, leading researchers to revisit older datasets with increasingly advanced methods. Sometimes a signal that once appeared meaningful vanished completely after recalibration and reanalysis. In other situations, the signal remained uncertain because the background noise was simply too strong to support a confident conclusion. With each new study, the challenge of separating extremely faint signals from ordinary statistical fluctuations became even more obvious. Even the locations chosen for observation created additional complications. Areas believed to contain high concentrations of dark matter, often also hosted many energetic astrophysical processes, making interpretation far more difficult. Meanwhile, regions with relatively quiet astrophysical environments usually contained lower amounts of dark matter, reducing the likelihood of detecting any signal at all. Balancing these competing factors required researchers to carefully choose observational targets and continuously refine their observing strategies. Some investigations concentrated on individual galaxy clusters whose mass distributions had already been studied in detail. Others combined observations from multiple dwarf galaxies simultaneously in order to improve the statistical significance of possible signals. Despite all these carefully designed methods, the results continued to remain uncertain and inconclusive. Computer simulations still played an essential role in helping scientists interpret what they observed. These simulations offered valuable insight into how dark matter could behave under different physical conditions, and helped researchers estimate what kinds of signals might realistically appear. They included gravitational influences, particle interactions, and complex astrophysical processes together within the same calculations. By comparing computer-generated simulations with real observational measurements, scientists could evaluate whether a specific theoretical model accurately reflected reality. In many situations, the results suggested that any self-interactions involving dark matter had to remain extraordinarily weak in order to avoid conflicting with observations of colliding galaxy clusters or the internal motion of galaxies. This ruled out theories predicting strong interactions, yet it still left an enormous range of possible explanations available. The slow build-up of negative or inconclusive findings did not reduce the value of the investigation. Every experiment sharpened the scientific understanding of what dark matter might actually be. Each quiet setback reduced the number of viable possibilities, gradually steering researchers toward ideas that aligned more closely with the observed behavior of the universe. The absence of clear signals did not completely eliminate the possibility of dark matter interactions. It simply suggested that such interactions were probably extremely faint, exceptionally uncommon, or limited to environments and conditions that current observations still could not reach. Because of this, scientists continued concentrating on increasing detector sensitivity, broadening the range of astronomical observations, and developing entirely new methods of detection. Beyond examining distant cosmic structures, researchers also explored whether dark matter interactions could reveal themselves through signals that changed over time. Certain theories proposed that the concentration of dark matter near Earth might vary slightly, producing periodic fluctuations in detector readings. Experiments therefore began searching for annual modulation, a tiny shift in detection rates caused by Earth's motion as it travels through the galaxy. One research project reported a repeating modulation that appeared consistently across many years, attracting considerable scientific attention. However, other detectors using comparable techniques failed to detect the same effect. This disagreement sparked ongoing debates over whether the modulation represented genuine dark matter interactions or whether it resulted from environmental influences or instrumental noise. The possibility remained unresolved, but without independent verification, certainty remained out of reach. New generations of instruments were designed to search for even weaker and more delicate signals, extending sensitivity far beyond earlier limits. Some experiments focused on detecting phonons, microscopic vibrations inside materials produced by extremely small energy deposits. Others concentrated on identifying lightweight particles that previous searches may have overlooked entirely. These approaches expanded the range of possible signals researchers could investigate, while simultaneously revealing how difficult it was to separate authentic events from ordinary background interference. Every new technique carried both the hope of discovery and the strong possibility of yet another quiet disappointment. Even with these challenges, the search played an essential role in guiding theoretical physics. As observational boundaries became increasingly strict, theorists revised and reshaped their models accordingly. Ideas that once appeared highly convincing gradually became less plausible, as experimental data contradicted their predictions. In response, Newer theories emerged that better satisfied the updated constraints. This constant exchange between observation and theory allowed progress to continue even in the absence of direct evidence. Dark matter still remained unidentified, but the limits surrounding its possible behavior became clearer with time. Whatever this invisible mass was, it had to obey increasingly narrow conditions, influencing how future experiments were designed and where researchers directed their attention. As more years passed and experiments repeatedly produced results that reduced the list of dark matter candidates without definitively confirming any of them, some scientists began considering another possibility entirely. Perhaps the unseen mass inferred across the cosmos was not composed of a new particle after all. Instead, maybe the fundamental laws governing gravity behave differently under certain circumstances. This proposal did not emerge because physicists lost interest in particle-based explanations, but because gravity itself remained notoriously difficult to examine under the extreme conditions present on cosmic scales. Most areas of physics involved forces that could be studied directly in laboratories, but gravity, despite shaping the structure of the universe, was by far the weakest of the four known forces and often resisted precise testing in many environments. If gravity changed slightly across enormous distances or under conditions involving extremely low acceleration, it could potentially create effects similar to those normally attributed to invisible matter. This idea encouraged researchers to investigate alternatives that modified gravitational behavior rather than introducing entirely new forms of matter. Much of the motivation behind these alternative theories came directly from the strange rotation patterns observed in galaxies. Stars located near the outer edges of galaxies were traveling far too quickly to remain gravitationally bound if only visible matter existed. One explanation proposed that a massive invisible halo surrounding galaxies supplied the additional gravitational pull required to keep those stars in orbit. Another possibility suggested that gravity itself became stronger or behaved differently when accelerations became extremely small. If gravity failed to obey the standard inverse square law under such conditions, then the unusually high stellar speeds might no longer require additional unseen mass at all. One of the earliest and most widely debated alternatives suggested that gravitational acceleration experienced a subtle modification at extremely low levels. This approach did not reject gravity itself, but instead argued that the familiar laws governing it required slight adjustments in specific situations. The concept gained attention because it tried to account for the behavior of galaxies without requiring enormous amounts of invisible matter. This method managed to explain certain galactic rotation curves surprisingly well. By altering the traditional understanding of gravitational acceleration, scientists found that the movement of stars in many galaxies could follow expected patterns without introducing dark matter. Those early results inspired researchers to continue investigating the idea further. Scientists studied how these modified gravitational laws behaved across different galaxies, and in many cases, the calculated motions aligned closely with the observed rotation curves. Yet, although the approach appeared encouraging on smaller cosmic scales, difficulties emerged once it was applied to larger systems. Galaxy clusters became one of the biggest obstacles. The gap between visible matter and the gravitational effects observed within clusters was far greater than the discrepancy seen in individual galaxies. Even after modifying gravity, some additional unseen mass still appeared necessary. The same corrections that successfully described galaxies failed to resolve the inconsistencies found on cluster scales. Gravitational lensing created another important challenge. If gravity truly operated under different rules, then the way light bent around galaxies and clusters should also reflect those altered behaviors. However, lensing observations frequently matched models that included halos of dark matter far more closely than models based only on modified gravity. This became especially problematic in merging galaxy clusters, where ordinary visible matter separated from the regions producing the strongest gravitational effects. In those systems, the gravitational signal tracked the galaxies instead of the gas, implying the existence of a type of mass that behaved differently from ordinary matter. Modified gravity theories struggled to explain this separation naturally, unless extra assumptions were introduced, making the models more complicated than originally intended. Researchers kept refining these alternative theories in hopes of bringing them into better agreement with observations. Some scientists introduced increasingly sophisticated mathematical corrections to the way gravity behaved across different scales. These refinements achieved certain successes, particularly when describing individual galaxies, but they often demanded careful fine-tuning that weakened the original appeal of simplicity. A framework that accurately explained one category of cosmic object frequently failed when tested against another. Because the universe contains such a wide range of structures, any replacement for dark matter needed to remain consistent across many different environments, from tiny dwarf galaxies to enormous galaxy clusters, and from the fluctuations of the early universe to the structures visible today. Another major observational problem came from the cosmic microwave background. The tiny temperature variations spread across this ancient radiation formed shortly after the birth of the universe. Their characteristics depended strongly on how much mass existed during that early era. Theories attempting to eliminate dark matter while changing gravity found it difficult to reproduce these fluctuations correctly. Considerable adjustments became necessary to match the observed patterns, including the relative heights of the peaks within the fluctuation spectrum. Dark matter models reproduce these features naturally with only minimal additional assumptions. By comparison, modified gravity approaches often required many extra parameters, making them appear less elegant from the standpoint of theoretical simplicity. The large-scale cosmic web introduced yet another complication. Simulations demonstrated that without dark matter, or at least without some mechanism capable of producing comparable gravitational effects early in cosmic history, the enormous filaments linking galaxies and clusters would fail to form in the observed way. Modified gravity theories attempted to generate these structures by changing the behavior of gravity itself, but the calculations became progressively more intricate. Simulations needed to include multiple layers of gravitational rules that varied according to environment, scale, and acceleration. Even then, several versions could not reproduce the same density contrasts seen in actual astronomical observations. Other models generated structures that appeared too diffuse or arranged differently from what galaxy surveys revealed. Even with these difficulties, scientists continued exploring such ideas because gravity remained one of the most fundamental pieces of cosmology. Researchers returned repeatedly to the equations describing gravitational force and questioned whether extensions to general relativity could create effects that resembled dark matter. Some theories suggested that gravity might possess an extra large-scale component, similar to how earlier discoveries uncovered hidden aspects within other physical forces. These proposals did not always remove dark matter completely, but instead attempted to divide the explanatory burden between unseen mass and modified gravitational behavior. In several models, gravity included additional fields or mathematical terms that changed how it operated, depending on distance or local matter density. This allowed gravity to behave one way inside galaxies and another way inside clusters, helping address some of the weaknesses found in simpler modifications. These expanded theories generated a wide variety of predictions. Certain versions successfully reproduced galactic rotation curves while remaining compatible with gravitational lensing measurements. Others attempted to model the cosmic microwave background more accurately. Yet despite all these efforts, achieving agreement across every major observation continued to be extremely challenging. The intricate structure of the universe required a theory that could explain many different phenomena without producing contradictions. As alternative gravity theories became increasingly advanced, dark matter still remained the more straightforward explanation for a wide range of observations. The idea of invisible mass could be applied consistently across enormous cosmic scales, whereas modified gravity models often needed to adjust their behavior differently depending on the situation being examined. Another major difficulty for modified gravity appeared in the study of merging galaxy clusters. When astronomers observed clusters colliding and passing through each other, they discovered a separation between the visible gas and the regions containing most of the gravitational influence. Gravity appeared to stay aligned with the galaxies rather than the gas itself. Under a modified gravity framework, Gravitational effects should generally trace visible matter unless unusual additional conditions were introduced. Some theories tried to solve this issue by adding extra fields that followed galaxy positions differently from gas distributions. But every added mechanism increased the complexity of the models. With each new adjustment, the theories became harder to defend, compared with the simpler explanation that galaxy clusters contained enormous quantities of unseen matter. As these alternative gravity models grew more elaborate, researchers began comparing how many assumptions each explanation demanded. The dark matter hypothesis introduced an entirely new type of matter while leaving the existing laws of gravity untouched. Modified gravity approaches, meanwhile, preserved ordinary matter physics but required new gravitational rules, corrections, or additional fields. Both perspectives added something unfamiliar to physics. The debate gradually shifted toward explanatory efficiency. Which idea could explain the largest number of observations with the fewest assumptions? For many scientists, dark matter offered the cleaner and more effective answer. Even so, the study of modified gravity remained extremely valuable. It expanded scientific understanding of how gravity might operate under unusual conditions and encouraged researchers to challenge assumptions that otherwise may have remained unquestioned. It also motivated the creation of increasingly precise tests capable of separating modified gravity explanations from dark matter scenarios. Many of these tests relied on detailed measurements of gravitational lensing, galaxy rotation, or the behavior of systems containing very little visible matter. Certain galaxies with extremely small numbers of stars became useful natural laboratories for these investigations. If gravity truly changed behavior under very low accelerations, those galaxies should display the effect clearly. Observations of these systems allowed astronomers to evaluate whether modified gravity models could successfully reproduce the data. Some models achieved partial success, but many encountered difficulties when tested across the full diversity of galactic environments. Additional studies focused on the internal motions of stars moving within galaxies. Modified gravity theories predicted precise relationships between how matter was distributed and how quickly stars should travel. Although some galaxies matched these predictions quite well, many others showed behavior that differed from the expected trends. Dark matter, because of its adaptable distribution and flexibility, accounted for those irregularities much more naturally. As astronomers continued observing more galaxies, the diversity in galactic structures became increasingly apparent. Modified gravity models needed to explain all of these systems consistently, which remained a persistent challenge. Despite the obstacles these theories faced, the investigation of modified gravity encouraged broader and deeper thinking about the universe itself. It pushed researchers to consider whether cosmic phenomena might expose hidden properties of gravity not yet fully understood. Even if modified gravity theories never replaced dark matter entirely, the effort still strengthened scientific understanding of how gravitational laws might eventually be refined or extended. Some researchers even proposed hybrid theories that combined aspects of dark matter with elements of modified gravity. These speculative models attempted to preserve the advantages of both approaches while minimizing their weaknesses. Though highly theoretical, they represented attempts to build more unified explanations of cosmic behavior. As modified gravity research continued evolving, it also became connected with studies of dark energy, the mysterious phenomenon responsible for the accelerated expansion of the universe. Certain theoretical frameworks tried to link dark matter and dark energy within a single model by modifying gravity in ways capable of explaining both effects simultaneously. These ideas remained early and uncertain, but they demonstrated how deeply interconnected cosmic mysteries could become. Although dark matter and dark energy appeared as separate phenomena observationally, both pointed toward possible gaps in humanity's understanding of gravity and large-scale cosmic structure. The development of alternative gravity theories reinforced the necessity of questioning every assumption carefully. Scientists could not simply accept dark matter automatically without also examining whether gravity itself behaved differently on scales vastly larger than anything experienced in ordinary life. This constant scrutiny helped keep the dark matter hypothesis strong because it was repeatedly tested rather than blindly accepted. Every new experiment or observation involving gravity created opportunities to sharpen scientific understanding, discard weaker ideas, and reinforce the foundations of modern cosmology. At the same time, the steadily increasing number of successful predictions generated by dark matter models, especially when supported by large cosmological simulations, made those models increasingly difficult to replace. Modified theories of gravity were capable of reproducing a few specific effects, but they consistently struggled to explain the enormous collection of observations gathered throughout decades of research. The separation between visible matter and gravitational mass inside galaxy clusters, the distinctive signatures found in the cosmic microwave background, the enormous architecture of the cosmic web, and the motions observed within galaxies all matched far more naturally with the existence of invisible mass. In many situations, introducing an unseen type of matter proved simpler and more effective than completely rewriting the laws of gravity themselves. Even so, modified gravity theories remained extremely useful as comparisons. Any successful explanation of the universe had to equal or surpass the explanatory strength provided by dark matter models. By investigating alternative ideas, scientists were able to probe the boundaries of what gravity on its own might achieve. This process of comparison ultimately reinforced confidence in dark matter, while also exposing places where our understanding of gravity could still require adjustments or refinement. From the earliest evidence hidden within galaxy rotation curves to the immense network of the cosmic web stretching across billions of light years, the effects of dark matter have appeared repeatedly in ways that shape the universe much more deeply than the ordinary material visible to us. And yet, this substance that controls motion across the largest scales never interacts with us in any ordinary or familiar way. It surrounds Earth, passes through it continuously, occupies the vast distances between stars, and influences the birth of every major structure that has ever formed. But it does all of this silently, without leaving traces our senses or common instruments can directly notice. The strange contradiction lies in the difference between its overwhelming importance and its refusal to interact openly with the world around us. Even so, its existence can still be followed through consequences so consistent and widespread that its influence becomes impossible to ignore in almost every astronomical observation ever made. The ordinary matter we recognize, atoms, molecules, dust, gas, planets, and stars, forms structures, because gravity pulls material together over time. That entire process depends strongly on how mass is arranged throughout space. In places where large amounts of mass exist, gravity grows stronger, allowing gas to collapse more easily into stars and galaxies. In regions containing very little mass, the process slows dramatically, leaving behind enormous stretches of nearly empty space. Dark matter determines where many of these regions develop. Long before the first stars ever appeared, dark matter had already gathered into dense clumps that created gravitational wells powerful enough to pull ordinary matter inward once the young universe cooled. These ancient structures could not be seen directly, yet they shaped everything that came afterward. As gas slowly fell into those invisible wells, galaxies eventually emerged at their centers. Without those early gravitational foundations, the observable universe would appear completely different from the one we see today. This same pattern repeats itself across every scale in the cosmos. On the smaller level of individual galaxies, the arrangement of dark matter influences how quickly stars travel, how stable their orbits remain, and how galaxies evolve through time. A galaxy containing a dense concentration of dark matter near its center can hold its stars more tightly, creating rotation curves that preserve high speeds far beyond the visible boundary of the galaxy itself. A galaxy with a weaker or more spread out concentration of dark matter displays an entirely different rotational behavior. Even the shapes of galaxies reveal the presence of this hidden structure. Spiral galaxies with long, extended arms depend upon the support of a surrounding dark matter halo to preserve their form. Without that invisible support, those arms would gradually unwind and lose their familiar appearance over immense spans of time. Whenever astronomers attempt to model the internal structure of galaxies, they repeatedly discover that visible matter alone cannot reproduce the motions telescopes actually observe. Simulations using only stars, gas, and dust generate galaxies that behave very differently from real ones. These computer-generated galaxies lack the stability visible in nature, and their outer regions begin slowly drifting apart. But when dark matter is included in the calculations, the results suddenly resemble real observations much more closely. The gravitational field, created by the unseen mass, supplies the extra support required to preserve the galaxy's shape and regulate its internal behavior. Stars move the way they do because the surrounding halo shapes the gravitational environment through which they travel. Beyond the scale of individual galaxies, dark matter continues shaping cosmic structure in ways ordinary matter alone cannot accomplish. Galaxy clusters, among the largest gravitationally bound structures in the entire universe, contain enormous quantities of dark matter, exceeding the combined mass of all visible galaxies inside them. Dark matter creates the deep gravitational foundation of the cluster itself, determining how galaxies move within it and how the structure changes over time. Observations of galaxy clusters repeatedly show that the distribution of mass almost never matches the visible galaxies alone. Instead, gravitational lensing reveals huge regions of hidden mass extending far beyond the glowing matter we can directly observe. These enormous extended regions reveal the way dark matter shapes the entire environment of a galaxy cluster, drawing galaxies inward and affecting the paths they follow through space. Clusters frequently undergo mergers, moments when two or more massive cosmic structures crash into one another. During these encounters, dark matter becomes essential in determining how the clusters move through each other. Since dark matter barely interacts with anything besides gravity, it travels through the collision almost untouched, continuing along with the galaxies themselves. At the same time, enormous clouds of gas inside the clusters collide directly, slowing down, heating intensely, and becoming visible through X-ray observations. The clear separation between the hot gas and the total gravitational mass offers strong evidence that dark matter controls cluster dynamics independently from ordinary visible matter. The gas reacts violently to the collision, while the invisible mass continues advancing forward, carrying galaxies along with it. This behavior strengthens the conclusion that most of a cluster's mass is made of something that interacts only very weakly with normal matter. The influence of dark matter stretches even farther, serving as a major force behind the formation of the cosmic web itself. Although galaxies visually outline this giant network, the underlying structure originates from unseen mass. The web emerged when tiny density fluctuations from the early universe slowly expanded under the pull of gravity. Dark matter, unaffected by radiation and interacting almost entirely through gravity alone, started gathering together first, building vast filaments and massive nodes across space. Visible matter later followed these invisible frameworks once it cooled enough to condense. The arrangement of galaxies across billions of light years mirrors the hidden architecture created by dark matter. Even the enormous cosmic voids, regions containing very few galaxies, depend on the way dark matter accumulated around them. If the characteristics of dark matter had differed even slightly, the entire structure of the cosmic web might have formed in a completely different way. If its particles moved more rapidly, smaller structures would not have appeared early enough. If they traveled too slowly or interacted too strongly with each other, matter could have clumped together far too densely. The balance observed throughout the universe reflects the particular behavior of dark matter, combining weak interaction, moderate movement, and gravitational influence. That balance allowed the universe to evolve into the distribution of galaxies astronomers observe today. Beyond shaping where matter gathers, dark matter also controls how galaxies develop over time. When two galaxies collide or merge together, their visible parts may pass through each other, interact violently, or trigger the birth of new stars from disturbed clouds of gas. Beneath all of that activity, however, the dark matter halos surrounding those galaxies merge in ways that ultimately determine the final structure of the combined system. These halos pull matter inward, reshape the gravitational environment, and guide how the visible galaxies eventually settle. Many features seen in large galaxies today, including broad halos of stars and streams of disrupted material stretching through space, preserve evidence of earlier interactions controlled by dark matter halos. Those halos hold the memory of ancient mergers, continuing to influence how stars and gas are distributed long after the visible traces of the collision have faded away. Even in distant regions surrounding galaxies, dark matter still shapes gravitational conditions. The movement of small satellite galaxies orbiting larger galaxies depends heavily on the mass of the dark halo surrounding them. Observations of these satellites reveal gravitational forces far stronger than visible matter alone can explain. Dark matter acts as the unseen anchor holding these smaller systems together. In certain situations, the arrangement of dark matter determines whether a satellite galaxy survives intact or becomes stretched into long streams of stars. These tidal streams help astronomers trace the size and reach of the surrounding halo, revealing how far it extends beyond the visible edges of a galaxy. Another important effect of dark matter appears in the way galaxies gather into groups and clusters. Gravity pulls galaxies toward one another, but the speed of this process and the distances maintained between galaxies depend on the total amount of mass in the region. Only when dark matter is included can computer simulations successfully reproduce the clustering patterns astronomers actually observe. The structures of galaxy groups, their shapes, and the motions they display all match models requiring enormous amounts of unseen mass between and around visible galaxies. Without dark matter, clusters would form more slowly, appear less organized, and contain much weaker gravitational structure. Dark matter also plays a role in the expansion history of the universe itself. While dark energy drives the accelerated expansion of space, dark matter still contributes a large portion of the universe's total gravitational pull. The balance between dark matter and dark energy affects the speed at which cosmic structures emerge and evolve. If dark matter did not exist, or if its properties were significantly different, the expansion history of the universe would appear completely altered. Galaxies might still come into existence, but their formation, times, and overall distribution throughout space would change dramatically. The cosmic microwave background preserves evidence of this balance as well. Tiny temperature variations within that ancient radiation provide a snapshot of conditions in the early universe, revealing how matter was clustering during that distant era. These variations depend strongly on how much dark matter exists, and the observations match remarkably well with models containing far more dark matter than ordinary visible matter. Even though dark matter influences nearly everything on cosmic scales, it never encounters us in any familiar or traditional way. It does not interact with atoms through chemical processes or electromagnetic forces in a manner that allows easy detection. Because of this absence of interaction, dark matter moves through Earth constantly, without attracting any notice at all. Its particles travel through the planet almost as though the world were largely empty space. They pass through the atmosphere, the oceans, the crust beneath our feet, and even through human bodies without leaving visible traces behind. The instruments designed to search for signs of their existence depend on incredibly rare collisions that may happen only once over many months or even years, despite using enormous amounts of highly sensitive material. The reality that dark matter can shape the universe while remaining detached from our immediate surroundings creates a very unusual circumstance. It is deeply connected to everything on cosmic scales, yet entirely removed from the ordinary experiences of daily life. Stars are able to form because dark matter helped create the galaxies that contain them. The movement of the Milky Way through space follows the gravitational influence of invisible mass spread throughout and around it. Even the distant future of the universe depends partly on the balance between dark matter and dark energy. Yet none of these influences appear in ways that people can directly sense for themselves. Gravity operates across immense distances and enormous stretches of time, which means the effects of dark matter become visible only through detailed observations and precise measurements. This divide between influence and interaction makes the study of dark matter extremely difficult. Since it refuses to interact with visible matter in any meaningful way beyond gravity, scientists are forced to rely on indirect approaches to investigate it. Astronomers examine motion, gravitational lensing, and the growth of large cosmic structures in order to determine where dark matter may be located. Experimental researchers construct sensitive detectors in the hope of observing exceptionally rare collisions. Theoretical physicists develop models predicting how dark matter could behave if entirely new forms of matter truly exist. Every one of these methods reveals part of the larger mystery, but none of them offers a complete picture. Dark matter shapes the universe on every scale while remaining completely silent about what it actually is. Even so, its gravitational influence forms the foundation for almost every large structure that exists throughout the cosmos. Without dark matter, galaxies would not emerge in the same forms or numbers we observe today. Stars could still exist, but the universe would lack the enormous network of filaments and dense nodes that define the large-scale arrangement of matter across space. Galaxy clusters would possess far less strength, and many smaller satellite galaxies would no longer remain gravitationally bound to larger systems. The balance of gravity between galaxies would change dramatically, altering the future development of cosmic environments over immense periods of time. Dark matter does not need to directly interact with ordinary matter, because gravity alone allows it to reshape the universe across billions of years. The fact that dark matter controls these enormous cosmic patterns, while remaining absent from familiar interactions, reveals how much of reality operates far beyond everyday human experience. The visible universe represents only a small fraction of what truly exists. Ordinary matter creates light, forms planets, and builds the structures human beings can observe, but it is not the dominant ingredient guiding the evolution of the cosmos. Dark matter occupies that position instead. Its gravitational pull establishes the framework upon which all cosmic events unfold. Everything else, including the matter that eventually forms stars, planets, and living beings, develops within the structure created by this invisible mass. The long effort to understand the unseen substance shaping the universe has repeatedly led researchers back to a question that refuses to disappear, not because the evidence supporting dark matter is weak, but because the evidence itself encourages deeper examination. For decades, astronomers and physicists have carefully tracked the influence of something invisible, something that controls motion so consistently that it has become essential to every modern cosmological model. Yet, despite this overwhelming agreement across observations, the invisible material itself has never been directly detected. No experiment has successfully captured it inside a detector, identified it within a confirmed signal, or observed it interacting with ordinary matter in any way other than gravity. This creates a tension between what the universe appears to require and what scientific instruments have actually been capable of confirming. Inside that tension rests an important question. Does dark matter truly exist as a physical substance within the universe? Or are the observations pointing instead towards something entirely different, something still unrecognized because the assumptions guiding the search have also shaped the conclusions being reached? This question does not emerge from skepticism for its own sake. It exists because every attempt to uncover the particles believed to compose dark matter has so far ended in silence. Extremely sensitive detectors hidden deep beneath mountains have searched patiently for rare collisions and detected nothing conclusive. Telescopes operating in space have monitored the universe for unusual emissions, only to find signals that generally align more closely with ordinary astrophysical explanations instead. Particle accelerators have tried to generate invisible particles by reproducing the extreme conditions that existed in the early universe. Yet the outcomes have continued to remain consistent with established physics. These restrained results do not disprove the possibility of dark matter, but they do highlight something important. If dark matter truly represents a new category of matter, it may be so difficult to detect that present-day technology cannot yet reach it, or it may exist in a form entirely unlike the possibilities scientists have tested until now. At the same time, the universe continues behaving in ways that visible matter alone cannot explain. Galaxies spin far too rapidly at their outer edges. Massive galaxy clusters remain bound together despite displaying much less observable mass through stars and gas than their gravity suggests. Light curves around galaxies and clusters more dramatically than visible material alone should allow. Large cosmic structures appear earlier and develop more efficiently than ordinary matter by itself can account for. The cosmic microwave background contains patterns that demand extra mass which does not interact with radiation. These clues emerge from completely different environments, depend on different measurements, and involve different instruments and observational techniques. Even so, they all indicate the existence of something massive that remains invisible to light. This remarkable consistency has turned dark matter into one of the foundational elements of modern cosmology. The challenge comes from understanding the true nature of that foundation. Evidence supporting dark matter is indirect, inferred through gravitational influence rather than direct observation. Astronomy has relied on this kind of reasoning before. Neptune was identified because its gravity subtly disturbed Uranus, revealing its existence before astronomers actually saw it. In that sense, the reasoning behind dark matter is not unusual. The difference is that Neptune was eventually observed directly, confirming the prediction. Dark matter has still not reached that stage. Its gravitational fingerprints appear undeniable, yet whatever creates those effects continues to remain hidden. This leaves scientists in a strange situation where dark matter seems strongly supported by evidence while still lacking final confirmation. Yet the expectation that it must eventually appear in detectors may not reflect its true character. It may not interact with ordinary matter in ways capable of creating measurable signals. It may not strike detectors, decay into particles we can identify, or transform into photons within magnetic fields. It could represent a form of matter fundamentally unlike anything humanity has encountered before, requiring completely different theories and detection methods to investigate properly. If that is the case, then the lack of direct detection does not necessarily mean it is absent. Instead, it may simply expose the limitations built into the assumptions guiding the search itself. Another possibility is that dark matter is not composed of a single particle species, but instead consists of several different components. The visible universe already contains many forms of matter with very different properties, so it would not be surprising if the invisible universe possessed similar diversity. If dark matter were made of multiple particle types with different masses, velocities, and interaction strengths, then identifying any individual component could become far more difficult. An experiment designed to detect one kind of interaction could completely overlook another. This possibility would preserve the gravitational consistency astronomers observe, while also explaining why direct detection efforts continue failing. However, it would also greatly increase the complexity of the problem, demanding theories capable of describing an entire hidden sector containing multiple unfamiliar particle families. In contrast to these possibilities, some scientists question whether the unseen mass truly needs to be interpreted as physical substance at all. If gravity itself changes behavior under specific conditions, perhaps these observations reflect modifications in gravitational laws rather than the influence of unknown matter. Modified gravity theories argue that gravitational attraction in low acceleration regions, such as the outskirts of galaxies, may not behave according to traditional expectations. If that were true, stars could orbit faster without requiring additional hidden mass. Although certain modified gravity models successfully reproduce some observations, they struggle to explain others. Galaxy clusters especially remain difficult to describe without extra unseen mass. The cosmic microwave background also imposes strong limitations that modified gravity alone cannot fully satisfy unless additional assumptions are introduced. These difficulties do not eliminate the concept entirely, but they suggest that if gravity is being misunderstood, the correction would need to be far more complicated than originally imagined. There is also the possibility that both dark matter and modified gravity play roles in shaping cosmic behavior. Under this perspective, Dark matter exists, but gravity itself may also contain features absent from the simplest theoretical models. These hybrid approaches attempt to merge the strengths of both ideas, explaining the motion of galaxies while still preserving the requirement for additional mass within clusters and large-scale cosmic structures. This line of thinking is appealing because it leaves room for flexibility, yet it also carries the danger of becoming so adaptable that making precise, testable predictions becomes increasingly difficult. Even so, the concept reflects the larger uncertainty surrounding the actual source of the gravitational effects scientists continue measuring throughout the universe. The issue of whether dark matter truly exists in a literal physical sense becomes closely tied to the way observational evidence is interpreted. Astronomers measure gravitational influences, chart the movement of stars and galaxies, and examine the arrangement of enormous cosmic structures. Those measurements themselves are objective and consistent. What changes is the theoretical framework chosen to explain what those measurements mean. For many decades, the assumption that invisible mass must consist of some unknown form of matter has directed scientific research, and the evidence gathered so far strongly supports that interpretation. Yet the assumption itself still remains open to scrutiny, especially if the predicted particles continue avoiding direct detection. If observations keep expanding while experiments still fail to identify the particles responsible, scientists may eventually need to reconsider what these gravitational effects are actually revealing. Another important part of the discussion involves conditions in the early universe. The cosmic microwave background acts almost like a preserved image of the universe shortly after its beginning, revealing how matter was distributed during that era. The patterns observed within this background radiation depend strongly on both the quantity and the type of mass present at the time. Dark matter theories reproduce those patterns with remarkable accuracy. Models based on modified gravity can reproduce them only by introducing extra assumptions or additional components, many of which end up behaving in ways that resemble dark matter itself. This creates a curious situation where eliminating dark matter from the equations often requires replacing it with something functionally very similar. Even if the unseen mass ultimately turns out not to be matter in the traditional sense, any competing explanation must still imitate dark matter closely enough to match the observations already collected. That requirement significantly limits the range of possible alternatives. One of the more philosophical aspects of this question comes from recognizing that humanity's understanding of the cosmos has repeatedly expanded whenever entirely new forms of matter or previously unknown forces were discovered. There was a period when the concept of an electromagnetic field seemed unfamiliar and difficult to imagine. Later, quantum fields completely transformed how particles themselves were understood. The discovery of neutrinos revealed that enormous quantities of matter could exist while interacting only very weakly with ordinary material. If dark matter is real, it would continue this historical pattern by revealing that the universe contains additional forms of matter that remain invisible to light despite playing a major cosmic role. From this perspective, dark matter may simply represent the next stage in the ongoing refinement of physical theory. On the other hand, the question may point toward a deeper misunderstanding about gravity itself, or about the way mass behaves under extreme cosmic conditions. The enormous complexity of cosmic structures could involve features that existing theories still fail to describe correctly. If dark matter is not actually a physical substance, then the gravitational signals observed throughout the universe may instead be hinting at a more fundamental layer of physics that remains undiscovered. Pursuing this possibility requires investigating models that extend beyond general relativity or beyond the standard model of particle physics. These ideas remain speculative for now, but they demonstrate that the mystery cannot be resolved solely by collecting additional measurements. Progress also depends on developing entirely new concepts capable of explaining the same observations from a different perspective. There is also the possibility that dark matter is not one single phenomenon at all, but rather a placeholder term covering several unknown effects at once. The gravitational influences currently attributed to dark matter may originate from multiple separate causes. Some effects could come from undiscovered particles. Others may arise from hidden properties of gravity itself, Some might even reflect aspects of early universe physics that existing cosmological models have not yet fully incorporated. If several different mechanisms contribute to the invisible mass shaping the universe, then searching for only one specific particle type may never provide a complete answer. The continued silence from many detectors could simply reflect this mismatch between scientific expectations and reality itself. Despite all of these possibilities, dark matter models continue succeeding across an enormous range of observations, which is why they remain central to modern cosmology. From individual galaxies to massive galaxy clusters, from the structure of the cosmic web to the conditions of the early universe, invisible mass consistently provides explanations that align with the data while producing relatively few contradictions. If dark matter ultimately does not exist in the way scientists currently imagine, then any replacement theory would need to reproduce all of these successes while also providing deeper insight. That standard remains extremely difficult to meet, and so far, competing models have not consistently achieved it. This does not settle the debate permanently, but it does suggest that dark matter, whether it is a particle, a field, or something entirely different, still remains the simplest explanation, fitting the widest body of evidence available today. The question of whether humanity may be misunderstanding the situation becomes less about rejecting dark matter and more about recognizing the boundaries of present knowledge. Dark matter may truly be exactly what it appears to be, a form of matter interacting primarily through gravity and perhaps the weak force, existing in quantities vastly greater than ordinary matter. Or it could represent a network of assumptions guiding scientific research along one particular path, while other possibilities remain overlooked. The investigation continues because the universe keeps presenting new hints, each one leading back toward the same invisible gravitational effect, while still concealing the true nature of whatever is creating it. This lasting uncertainty does not weaken the importance of the evidence already collected. Instead, it reflects how scientific understanding naturally evolves over time. The biggest mysteries in science often remain unresolved for extended periods, moving through repeated stages of observation, interpretation, testing, and revision. The inability to detect dark matter directly has pushed researchers to improve and refine their experimental techniques. At the same time, the remarkable success of dark matter within cosmological models continues reinforcing the broader structure used to guide fresh observations and theoretical work. The balance between these two realities keeps the field active and flexible, willing to adapt when necessary while still remaining grounded in the gravitational evidence that first inspired the search. All of this gradually leads toward the understanding that explaining dark matter may require viewpoints humanity has not yet developed. The eventual answer could emerge from the discovery of an entirely new particle, a modified understanding of gravity, a more advanced picture of physics in the early universe, or perhaps some combination, connecting all of these possibilities together. Whatever form the explanation ultimately takes, the effect of this hidden mass on cosmic structure will continue directing scientific research, influencing the evolution of theories and creating new ways to investigate the concealed architecture of the universe, even while refusing to reveal itself through the ordinary signals associated with familiar matter. The search moves forward not because dark matter lacks credibility, but because the universe still appears to contain deeper layers of explanation waiting quietly to be discovered.